We'll go ahead and get started since it's 8:30, session 3, physics development and testing. And good morning and welcome. There's going to be 6 talks, 15 minutes per talk. And what I'll do is just, instead of doing the light about after 12 minutes, I'll just stand by one of the microphones as an indication and just try to leave time for questions. And with that said, let's go ahead and get started. The first talk is Pedro Jimenez, NSF NCAR, and he'll be telling us about some work on fire modeling in WRF.
Good morning. Hi. So I'm going to present our work entitled Coupling the Community Fire Behavior Model to WRF. And first of all, I would like to thank my collaborators, Anthony Islas, Michael Duda, Dan Rosen, and Jimmy Dudia, as well as other developers of the Community Fire Behavior Model, Maciej Dami, Maria Frediani, Michael Kabulich, Tim Giuliano, and Katie Wilson. This is the outline of the presentation. I will start by introducing the Community Fire Behavior Model. Then I will describe its coupling to the Unified Forecasting System when we started, and then the coupling to WRF. And finally, I will provide a summary and where we are heading. Our main idea with the Community Fire Behavior Model is to make it available to a variety of atmospheric hosts in order to foster collaborative development and raise the bar in fire science, and with the ultimate goal of mitigating the impacts of wildland fires. This is the model. We developed it to provide a fire behavior model to NOAA's Unified Forecasting System, UFS. And our first version, we started from the WRF, the version 4.3.3, and we closely follow on purpose the methods there. And the coupling with the atmosphere is done via the Earth System Modeling Framework, ESMF, and this requires having the fire behavior model into a National Unified Operational Prediction Capability, NUOPSI. And this essentially means that we need to have a subroutine to initialize the fire model and a subroutine to advance the fire model. And then a file that is referred to as the NUOPSI cap, where there is information about how to initialize the model, calling the subroutine, how to advance it, define the grid, and also define the variables that are exchanged between the fire and the atmospheric host. And this is done for all the Earth system components, and then the ESMF library is able to coordinate the advance of the different components. We can run it offline using an existing atmospheric state. We use WRF at this time. And also it can be run online, coupling to the atmosphere with the ESMF library, and soon we'll have a capability to run idealized simulations. I will introduce an example later. These are some characteristics of the fire behavior model. Again, is based on WRF 3.3, where the fire modules, but we did important reorganization of the code to create a standalone version. Those routines I was mentioning, defining the grid, writing our own output. And we also clarified the logic that is being done in the fire code. We had to remove atmospheric dependencies and we impose consistent format across the subroutines to improve readability. We implemented parameterizations of certain processes that we think we can improve in the future. And they're implemented as an abstract derived types and with the ferret type-bound procedures that we extend when we want to create a parameterization. And these are, at this moment, the rate of spread, fuel model, and the fuel moisture content model. The code is self-documented. I think it should be relatively easy for anybody to go there and understand what is done. We also remove a large number of checks and prints that were available in WRF to improve performance and reliability. And other minor things like improving geolocation. We impose implicit known statements all over all the procedures, and we eliminate variables that were past no use. And functions are declared pure whenever possible, and the code conforms to the Fortran 2008 standard. We also have some tests. Every time we do some developments, we run these tests. They are cheap and expensive. We run the model for a little bit, and we check the solution to ensure we don't break anything. The code is in a GitHub repository, and we have regression tests in place every time there is we push a commit. This is how the fire behavior model works. We start parameterizing the rate of spread of the model, which is a function of elevation, fuel characteristics, and other atmospheric surface variables. When we know how fast the fire is going to spread, we advance it, and to track the fire, we use the level set. This is a methodology that is used to track interfaces. And once we advance the fire front, we can ignite new cells and release heat, moisture, and smoke that can be connected to the atmospheric component. This in turn affects the winds, and in this way we have the coupled fire atmospheric model. That's how it works. Coming into UFS, this is how we couple. This is a very simplified diagram of UFS, and you see there right. I don't know how the pointer works. Right. So you see that on the left, the box, the NUOPC of the atmosphere in UFS. And I put just one other Earth system component of UFS, the ocean. You can see that it goes through the mediator. And these green arrows are the connectors, the variables that the models can exchange. And on the bottom row, you'll see the fire behavior model NUOPC. It has its cap like the other components, and you can see that it is directly coupled to the atmosphere. No need to go through the mediator. And we exchange these variables that I already mentioned: winds, temperature, and heat, moisture, fluxes from the fire and smoke. And then the SMAP libraries are able to coordinate the advance of the models. How does it work? This is an animation of simulation for one fire, the Cameron Peak. You see on the right the evolution of the UFS in one way, WRF one way, and the standalone mode, which reads the WRF atmosphere. And they are configuring one way, and you can see that they are evolving consistently. And this gives us confidence that we develop the model properly. On the left, you have the evolution of the fire area on top, and on the bottom, the wind speeds. You see that there's so similar variability with the winds and similar growth in the fire area. There are a couple more simulations there. There are simulations in WRF in two-way, and this WRF is WRF fire, and UFS in two-way, and you see that they are very similar to their one-way version, and this is because here we used 3 kilometers grid spacing, and the impact of the fire is very small at these grid spaces. This is an example of the idealized simulations, what we can do and how we are using it to make sure that the code is doing what we think we want to do. This is a simulation. Start from a fire line on the left, and the winds are to the right. And you can see this is the burn area, the perimeter, and ideally you should see a rectangle in this setup. And when you can see the different lines are different configurations of how we solve the partial differential equation of the level set. Ideally, we want to be in the theoretical solution that you see on the right, the dashed line. And you can see that depending on the flavor of the numeric we use, we are able to reach this point. So this is what we are using to make sure that the fire propagates at the intended speed. And also we are refining some aspects that we think there is room for improvement. Moving into WRF now, this is our strategy to couple it. The community fire behavior model is available as a Git submodule. And there is an automatic compilation with CMake. We are early adopters of this new technology. So far, we found it great because we didn't have to create the make files. That simplify and speed up our developments. And so the compile script fetches the code from the fire and automatically compiles both the atmosphere and the fire. We use existing WRF infrastructure to define the fire grid. So in this case, we don't use the ESMF software. We directly, since the coupling was there more or less in place for the WRF fire, it was in place. So we recycled this infrastructure. So the fire grid is a refined refined atmospheric grid. The fire state is a derived type, and then fire name list is also a derived type. And those are the only two objects that you need to move around to pass information and to propagate the fire. So we have included those derived types as part of the WRF derived type. This is the domain type, the grid that has all the information and all the variables in WRF. So in this way, our fire variables are automatically distributed through the code. We have very orthogonal coupling. We try to minimize the instances where we call the fire code. So there are only 3 points, where the first one is to read the fire name list. The second one is to initialize the fire state, and we need to pass on indices and a few variables describing the projection. And then the third one is the part where we advance the fire state. So here we need to interpolate the variable from the atmosphere to the fire grid, call the advanced state, and then we stop there because we have it coupling in just one way at the moment. The time step of the fire can differ from the atmosphere. This is desirable. We did it as we tested in the ALICE experiment. We want to have a smaller time step that 6 delta x being the atmosphere. So we can do that in our coupling. And the fire model is responsible for writing its own output. So we can customize the variables that we want in the atmosphere or in the fire. As I mentioned, we have a coupling one way. This is an example. We run the WRF coupled to this community fire behavior model and WRF fire, what is already there in WRF. And remember, we closely follow on purpose at this state the methods in WRF to ensure that we have consistent results. And this is what you can see here. This is the burn area of a given fire, and the pink region is 0. There's nothing burned there. The orange is all is burned in those grid cells. And those little colors, the colors that you see around is the perimeter of the active fire. And you can see that after 1 hour of simulation, both couplings, they have similar shapes. You go 27 hours into the simulation, again, with the consistency between the burnt area in the two models, and this gives us confidence that we are in the right direction with the coupling of the model with WRF. This brings me to the summary and future work. We have the community fire behavior model that we designed to facilitate interoperability with atmospheric models via the ESMF library. The code is publicly available. Here is the website of the model. You can download it from there. This site points you to the GitHub repository. We have it already in UFS, and we are now in the process of pushing to different UFS repositories to make it available to everybody. So we have started with CCPP, and we are in the internal process of reviewing that code to move on to push to other UFS repositories. We have coupled to WRF and one-way coupling at this moment, and we are going to extend it to two-way. At this point, there's no parallelization. We use just one core, so we have to extend the parallelization. And I think our idea is to have this probably released. We are pointing to have it in the next major WRF release, which will be, I think, in next spring. We have seen consistent evolution of the different models, and this is the starting point to further develop the model and to improve the realism and go to push the state of design to another level. looking into the future, further ahead, the coupling with MPAS, I think, should be straightforward. If MPAS adopts the ESMF libraries, then the coupling is essentially there. So I'll leave it there and I'll take questions. Thank you.
Yeah. Testing. Okay. We have time for one question.
I can't resist. You may have pointed this out just a little bit already, but I mean, if you're putting the heat fluxes back into the model, I'm not sure how realistic your heat fluxes are. And how much does that impact the stability in WRF? And how many, like with respect to time step versus horizontal resolution versus how many vertical levels?
So you do distributed. Well, our version still is not coupled to WRF. We are not passing the heat fluxes because it is one way. The way it's done in WRF right now is you distribute the heat in a number of vertical levels close to the surface. The user has the possibility to impose certain parameters, and it's a truncated Gaussian distribution, so you can decide how you want to distribute it there. But that's in the future for us. We didn't go there yet for WRF.
Okay, thank you. The next talk is Mengjian Liu from Nanjing University, China, and she'll be talking about planetary boundary layer schemes in the gray zone resolution area.
Thank you, Robert. Hi, everyone. I'm Mengjian, and today it's my pleasure to be here and share with you our recent progress on PBL scheme at gray zone resolutions. This work is supervised by my advisor, Bowen Zhou from Nanjing University. I know that the name is full of jargons, but don't worry, we're going to walk through it one by one. Start with PBL. We all know that PBL is a shallow layer between the surface and the free atmosphere above. And this layer is full of turbulent eddies of all sizes, but among them, the largest one, which also scales with the boundary layer height about 1 kilometer in daytime, are the energy-containing eddies, which these eddies are responsible for most of the transport of heat, energy, and materials from the surface to the free atmosphere. So if we want to model our atmosphere right, we need to model this energy-containing eddies right. But how? There exist two classical ways. If we are operating at very coarse resolution, like 10 kilometer in our global or mesoscale models, the grid spacing is so large that the energy-containing eddies are all subgrid scaled, and our 1D PBL schemes are doing a great job to do the parameterization. Well, on the other hand, if we are operating at very fine resolution, like 50 meter in our large eddy simulations, the energy-containing eddies can be well resolved, only remaining very tiny part to be subgrid scaled by these 3D models. But you can clearly notice that there is a big medium range in between them, where the size of the energy-containing eddies is comparable to the size of the grid spacing, could be 1 kilometer or even sub-kilometer. And we call this gray zone because here the eddies are partially resolved, but partially subgrid scaled, which makes our both PBL schemes and large eddy simulations both useless. And nowadays, it becomes a serious problem because all of our mesoscale and even global models are approaching this resolution. Like the MPAS-A is approaching at 3 kilometer and even 1 kilometer resolution. So how do we model this gray zone turbulence? Actually, this gray zone turbulence the idea is raised by John Wingard in 2004. So after 20 years, there rises a hierarchy of solutions. From the very theoretical end, we can calculate the tensor eddy viscosity. To the very practical end, we just insert stochastic signals to the model fields. But today, I would like to focus on the largest group among it, the scale-aware LES or PBL, which means that we augment the classical LES or PBL with the capability to regulate the subgrid scale fluxes in the gray zone. And you can see here there are a lot of literature. And actually, most of them are making use of a term called flux partition function. But what is flux partition function? This idea is first raised by Rachel Harnett et al. In 2011. In their figure, the x-axis is the gray spacing, normalized by boundary layer height, and the y-axis is the subgray scale and resolved fluxes normalized by total flux, which has a very good characteristic that it is invariant with respect to gray spacing. And when they plot all these points from different LES data and from different heights of subgray scale fluxes and resolved fluxes onto one plot, they found they are not like randomly scattered everywhere. Instead, they concentrate quite well into this X shape. And then they put forward this definition, this P variable, which is the subgray scale flux over the total flux, and fitted this concentrated X with two very smooth curve and call it flux partition function. This flux partition function is actually very powerful because it gives us the knowledge of how the subgray scale partition could be at any gray zone resolution we care about. And we already know the total flux because they are well simulated by our PBL schemes. By doing the simple multiplication, we will get the subgray scale flux we wanted in the gray zone. And actually, there are a bunch of schemes you can see here. They are all based on this flux partition function idea. And all the 3 scale-aware schemes you can find in WRF, they are also based on this idea. But if you dive into the codes a little bit more, you'll find the thing seems to be not that simple. It's not just a simple multiplication. Why? This is because this flux partition function actually includes multiple variables, not only the gray spacing. As we can see from Horner's figure, there are very distinct spread on both sides of the fitted curves. And due to a time issue, I don't have time to go through all these figures, but I want to say here is that this P is actually very height dependent, and we should not ignore the height dependence in our models. And what is worse, this P not only depends on gray spacing, height, but also on box stability of the boundary layer, and even the particular turbulent flux, which forbid the possibility to just set up a analytical simple formulation for the P, and then make our real implementation into gray zone schemes super complicated. Therefore, we're thinking of if there any possibility that we can form an univariate flux partition function. In that way, we only need one P function for one specific flux, and then we can largely ease the implementation of the flux partition function with our classical PBL schemes and in different models. So here are our theory. So in the established multivariate partition functions, we can find in existing papers, the gray spacing are usually normalized by boundary layer height. Here is Ci. This height actually stands for a very zeroth order approximation of the dominant length scale of turbulence. But actually, we know that the dominant length scale in boundary layer is quite different. They're varying with height and also varying with box instability. So we're considering if we can provide a better approximation of the dominant length scale, which can absorb both the dependence of height and box instability, and then we use this one to normalize our gray spacing instead of the boundary layer height. We can then absorb every multivariation into this one, and we form only one univariate, this non-dimensionalized group delta star for this P, so that we can realize this univariate P for each specific flux. So to study this idea, we need more data. So we construct a comprehensive large AD simulation data crossing the range of host convective boundary layer box stability from the free convection end to the neutral boundary layer end. And we use 2D Gaussian filter to cross-grain and generate the reference resolved and subgray scale fluxes from 10-meter resolution to 10-kilometer resolution. Now with this abundant data in hand, we can now study the characteristic length scales in convective boundary layers. And here shows you the two figures of different length scales we analyzed in these 11 different cases. And the upper one shows the results from heat flux. The lower one shows the results of the streamwise momentum flux. The left panel is the peak coef spectral wavelength. And the second one is the equal partition length. They're like two totally different independent manner. And we are very excited to see that So first, these two the left one and middle one, they share very similar shapes. And they also show the same trend of the variation with bulk stabilities as shown by the different colors, where the y-axis is the height normalized by boundary layer height. And the even better thing is we found for both two characteristic length scales, the profiles in different bulk stabilities have some similarity, which means if we try to squeeze them all to force them overlap each other as much as possible, we can remove the stability dependence and only subtract the height dependence one. And if we found that the squeezed profile happened to resemble well with the classical profile of peak wavelengths of vertical variance from Coggy and Palmer in 1979 as the fifth figure here. And so that we can borrow their mathematical form to form our height dependence in a similarity function. And the side product of doing the squeezing is we get coefficient for each bulk instability. So we plot the coefficient for both momentum flux and heat flux on one plot against the bulk stability. And we found the good thing is the momentum one and the heat one, they overlap each other quite well, which means we only need to fit one linear piecewise function to describe the stability dependence. Now that we can realize the height dependence and stability dependence into our dominant length scale, and we only need to use this dominant length scale to normalize our grid spacing instead of putting everything into our P. And we get a simplified P for both momentum flux and heat flux. And now it's the time to do the evaluation. So we start with offline. So we plot the parameterized P using this lambda as the dashed line for different resolutions from 200 meter to 1600 meter, which are all very typical one in gray zone, and compare with the reference results from LES, which are the solid lines. And we can see that at least beneath the entrainment zone, which can be noted here, the 0.8 boundary layer height, they matches quite well. Above that, it's not so satisfied, but considering about the small amount of subgrid scale flux there, it is still acceptable for us. And in fact, it is. When we estimate the subgrid scale fluxes using our P, we find that they match very well with the reference LES throughout the boundary layer for both heat flux and the momentum flux. Okay, everyone knows that offline is usually easier, so we move on to the online evaluation. So according to our theory, the univariate P can be incorporated to any traditional PBL scheme as long as it estimates the correct scale insensitive total flux. So as a proof of concept, we just implemented this P into the widely used PBL scheme YSU in our WRF. By doing the simple multiplication, we get a new scheme. This scheme is called SYSU, where S means scale, where S actually is just a implementation example. And then we compare the results of our model with the classic YSU, which is not designed for gray zone, and another established gray zone scheme already you can find in WRF, the SH scheme developed by Xin and Hong in 2015, together with the LES results. Here shows the profiles of subgrid scale heat fluxes for four very typical gray zone resolution from 200 meter to 1600 meter from left to right. And the upper and lower one stands for two different bulk stability cases. So here you can easily recognize the YSU line, which is the dashed one, because it's not designed for gray zone. So it's still simulating the total fluxes, even at 200 meter resolution. But we can hardly discern the other three profiles because they match each other so well, they overlap so well, which means that our simple implementation example, the SYSU scheme, is as good as the established gray zone scheme, and they are both well matched with the reference LES. And we can find similar results in the streamwise momentum flux profiles. And what is more encouraging to us is because we explicitly fitted the dominant length scale for momentum flux, we can quite well reproduce the profiles of the streamwise momentum flux at even very fine resolution like 200 meter and 400 meter, will overlap with the LES one. Okay. To sum up, we simplify the widely used flux flux partition function to an univariate one by absorbing the height and stability dependencies into the dominant turbulent length scale lambda. And now the simplified P becomes very highly portable, such that you can use this P in your own PBL scheme and make it your own gray zone scheme. And this work is already published in JAS this year, and all the formula of P and lambda and even the prototype SYC code, you can find it in the paper, and you're welcome to download and use it. And I'll stop here, and I'm happy to have questions. Thank you.
Do we have any questions?
Thank you. You're welcome to find me after the meeting.
Next talk is Wayne Angevine at University of Colorado, CRS, and he's going to talk to us about updates to the MYNN-EDMF scheme.
Yeah, good morning. I'm not giving my gray zone talk today. I wish I was. I have some fundamental disagreements with how people are handling gray zone, but that's not the talk I'm giving right now. So if you're interested in that, talk to me later. I will mention a couple of gray zone things in here. But what I'm talking about today is clouds in the MYNN-EDMF scheme and our addition of downdrafts, which Joe mentioned yesterday. Just to start with, I'm going to talk a little bit about clouds over the Pacific, some of which is what I showed last year, and then a new case, and then remind you a little bit about what EDMF is, and then talk about the downdrafts in concept and in the single column model tests that we're doing. So in our last episode, I talked about modeling of clouds over the Pacific. This is from the MAGIC campaign, which was in 2013. And I'm running a RAP-like configuration here. The physics is as much like RAP as I can make it. And on the left, you have the satellite picture from a particular time during the one really nice leg of that campaign. And on the right, you have the result on our 13-kilometer grid. And the keywords in there are 13-kilometer grid and effective resolution. Grid spacing is not resolution. I can't say that enough times. Grid spacing is not resolution. The reason that you have these large-scale blobs of cloud in the simulation here is effectively a gray zone issue. You have partially resolved circulations on this 13-kilometer grid, and the size of those blobs corresponds almost exactly to the effective resolution of the model, which is about 6 to 8 times the grid spacing. If I go to a finer grid, if I go to a 3-kilometer grid, it makes the structures smaller. They look more realistic. They're still grid dependent. Interestingly, the statistics, if you're interested in top of atmosphere radiation on a 1 degree by 1 degree grid, for example, are not very different. But it looks more realistic. So now we have 3-kilometer on the top, 13-kilometer on the bottom, and the satellite picture on the right. It also turns out to be the case that we can modify the strength and to some degree the size of those partially resolved circulations by tuning up or down the strength of the parameterization. So here's a newer case. This is from our Roma campaign from last summer, where we had a whole bunch of assets spread all over the country, really. This is showing a flight track of the NASA DC-8 that was heavily loaded with mostly chemistry instruments, but they were also interested in some cloud behavior. So again, on the left is the MODIS image, on the right is a simulation on the 3-kilometer grid. initialized from Era 5, which isn't perfect, but in general, we're getting a pretty good representation of the clouds there. And we think we can use that for some analysis of this campaign. And now this is what the very preliminary verification looks like. We've got a little bit of a cool bias in the temperature. The water vapor looks pretty good. Most of the variation you see there is from the airplane going up and down in altitude. The Scylla campaign, they had the Navy Twin Otter flying out of Southern California in some places where you can only fly if you're in the military. So this is preliminary data from one of those flights from that same simulation. And again, you see we've got a reasonably realistic representation of what's going on there. So to remind you a little bit about what EDMF is, we take a traditional TKE-based local mixing scheme and add updrafts to it. In the cartoon, there's only one updraft. In our actual implementation, we have 8 at the moment. This is what most of the centers around the world are doing for boundary layer schemes these days. It provides, I think, a very natural representation of boundary layer rooted clouds, as well as the updrafts themselves. However, not all boundary layers are surface driven. So sometimes the boundary layer is driven from the top, particularly in Stratocumulus, by radiative cooling at the cloud top, which then produces downdrafts. But downdrafts, it turns out, are not just upside down updrafts. The initialization is more complicated, and hitting the surface too hard can lead to numerical instability. You don't want to be generating microbursts unless you really want to be generating microbursts. So it turns out that you can't just turn your updrafts upside down and get a reasonable result, which I at least thought originally would be easier than it is. Also, the vertical grid spacing is coarser at the top at the inversion than it is near the surface. And the layer of cooling is very thin in these situations. So it's not obvious how you, where you should put the cooling layer or where you should initialize the downdraft. So we're trying to develop a downdraft subscheme. Joe mentioned it a little bit yesterday, and we need to test and improve it. So my candidate for testing is this large eddy ensemble of marine stratocumuli that has been produced by Graham Feingold's group, particularly by Yaosheng Chen and Taki Yamaguchi in our lab. So they've run 245 cases of non-precipitating stratocumulus, generating the members from perturbed initial profiles, running with interactive surface fluxes in a diurnal cycle, and they're doing this in SAM, which is a more or less dedicated large eddy simulation model because it's a lot faster than hydrostatic LES. And it covers a wide range of coupling states and diurnal behavior, and you can see the preprints for those 2 papers in ACP discussions. So here's just one case. I think there's a lot of power in having an ensemble because we can run more than one case. So far, I've only run 3, but we'll be looking at a lot more so that we're not overfitting to a single case. And now I'm comparing 2 WRF single column model runs with our physics. So the LES is in purple, and you can see that for this case, the cloud base and cloud top start out higher than they do in the single column model, and they rise over time. The cloud layer thins after the sun comes up. Running with downdrafts, what I call the base run here, we get a more or less static cloud base and cloud top. The LWP, the liquid water path, is a little bit small, and it increases through the day. And the cloud cover is kind of reasonable. If we turn the downdrafts off, which is what you would be getting right now by default in WRF, the cloud base actually decreases and the cloud thickens a little too much. And in this case, the In the base case, we get no updrafts in the single column model because the superadiabatic layer near the surface gets wiped out by the relatively strong downdrafts. You can see the profile is on the right. So what's actually going on inside the scheme? Now, in each of these three panels on the left, I've got on the far left, the vertical velocity. The panels from top to bottom are the updraft in the base run, that is updrafts in the run with downdrafts. In the middle, the updrafts in the case with no downdrafts, and on the bottom, the downdrafts in the downdraft case. I could probably figure out a more clever way to present this. The middle is the mass flux and the same thing. So what you can see there, if you can see it at all, is that there are weak updrafts in the downdraft case. There's basically nothing in the no downdraft case, and the downdrafts are doing almost all of the local mixing. I also put a plot of the QT variance, so the variance of total water on the right. And that is kind of just a check to see that the way we're diagnosing that in what Joe calls the level 2.6 scheme, which we use for looking at cloud amount, is looking reasonable in magnitude at least. So here's the well-known DICOMS case, a really pure stratocumulus case at night. And we see kind of the same behavior where the LES tends to want to increase the cloud base and cloud top, and the single column is holding it steady. With the downdrafts turned on in the base run, it thins the cloud very rapidly. In the no downdraft run, it doesn't. And the reason for that is because it's, as you can see from the profiles, it's almost completely decoupled. So there's really nothing going on in the cloud layer in the single column model. In the no downdraft case, it just sits there. Here's what the internals look like. So we have updrafts and downdrafts, but in the downdraft case, again, it thins the cloud pretty rapidly, and then the radiative cooling goes away, and so the downdrafts stop. So conclusions and further work. We have generally good performance for cloud systems over the Pacific. This is basically out of the box WRF 4.5. There's some room for improvement. In general, we think we have a bit of a low bias in cloud bases. It's hard to verify. The horizontal and vertical grid spacings matter a lot, even outside the traditional gray zone. Partitioning of energy and moisture between resolved and subgrid scales deserves more attention. And this is basically the gray zone issue, that the fundamental question is, how are you partitioning the available energy at the surface or at the cloud top between the resolved and the subgrid scales? And what does that do to the structures that you create in a 3D model? The downdraft subscheme is beneficial. We obviously need to do a bunch more development on it, and we're working on that. Looks like we need more entrainment at the cloud top, but we have to avoid destroying the cloud layers. And this is where the relatively coarse resolution of our vertical grid near the top may be part of the problem. So anybody who's tried it knows that translating results from research to operational configurations is non-trivial, and we're just beginning to do that with the downdrafts. So I'll stop there, and I'd be happy to take questions.
We have time for a couple questions.
Can't resist. For convection, updrafts, downdrafts are driven by buoyancy.
Mm-hmm.
The downdraft will be driven by evaporation of precipitation, which makes them another draft. It goes the other way compared to the updraft. It's not considered that second part of that one eddy, which is just subsidence. Is that the same way you're treating it?
Right now, we're not doing precipitation-driven downdrafts. We're only doing radiation-driven downdrafts.
But that's the same thing.
And Well, I'm not 100% sure that in implementation it's the same thing. We should sit down with Joe and talk about that. But right now we don't have precipitation inside the boundary layer scheme. That's part of the artificial separation that we have in model architectures. So, and I should say that I was running the GF convection scheme on those 3D tests that you saw. Where there was deep convection, the deep convection scheme was able to be active.
Radiation driven is important anyway, so.
Yeah, we think so, but you know, we know that we need to also handle the precipitation driven downdrafts.
Any other questions? Okay, thanks, Wayne. Oh.
Yesterday to you, having studied the KF schemes a lot, they have non-local downdrafts, in them. Have you leveraged that at all? I know if that's precipitation driven as opposed to radiation driven.
I haven't personally looked at that. We should ask Joe at some point what he has looked at, but yeah.
Thank you. Our next presenter is William Chang at NSF NCAR. And this will be a talk on PBL modeling, high resolution domains over complex terrain.
Thank you and good morning, everyone. I'll be talking about this work we're doing with the Colorado Department of Public Health and Environment. We're doing a 5-year reanalysis over the Colorado region with delta X of 1 kilometer. First, I want to acknowledge my co-authors, our colleagues at NCAR, Rajesh, who's our PI for the project, Gabby, Stefano, and the counterparts at the CTPHE, Miriam, or the program director at the CTPHE, and other colleagues at CTPHE, Sergio, Vijay, and Jennifer. Okay, as I mentioned, this is collaboration between the NCAR and CTPHE with a 1-year project from the Air Pollution Control Department to generate a 5-year 1 kilometer reanalysis over Colorado using the WRF-based CFDDA system. And currently, the APC is issuing the air quality permit with AirMod, just using the nearest meteorological observations. So by providing the 1 kilometer reanalysis, we hope to provide better input for AirMod or more representative for the meteorological conditions. How it works is that the WRF out files will be run through the mesoscale, the model interface, MMIF. We generate a surface file, an upper air file, and then it goes to AirMod, and then the output comes out as the air pollutant concentrations. And the PBL processes are one of the most important physics in the atmospheric dispersion models. For air quality applications, the stable conditions are of most interest. And in theory, the QNSE PBL scheme should work best under these conditions. But the QNSE hasn't been tested extensively for other conditions, for example, running for such a long period of time. And also over Colorado, we have meteorology complicated by complex terrains, such as like upslope wind and downslope wind, heating and cooling of the mountain. And so the purpose of this study is to test the sensitivity of the PBL schemes in WRF over the 1 kilometer domain over Colorado for different meteorological conditions before committing to a physics configuration for the 5-year reanalysis run. The CFDDA is actually a special application of our real-time 4-dimensional data submission system, RTFDDA. It started with funding by the US Army, and it's still being funded. Basically, it's a nudging system. We have an in-house FDDA that's different from the community. We have additional features such as weighting, quality control weighting for the observations, and also we're able to simulate observations below the model terrain. Different observational platforms can be the radio winds, the satellite winds, WM observations, wind profilers, mesonets, aircraft data, wind farms, other data, as long as it can be submitted by the model. And the arrow there's a conceptual diagram how it works. In the forecast system, we have the cycling, where during the analysis stage, you submit observations continuously when it's available. And recently, the CFDDA study that was applied over Southeast China with the finest mesh in 1 kilometer. The paper came out a while back. And the physics configuration we're using for the microphysics, we're using Thompson scheme, no convective parameterization for the 1 kilometer domain, land surface NOAA, short wave and long wave radiation with RRTMG, and with 8 different PBL schemes used in the experiments: the Bourgeois, Le Carré, Rennie, Bretherton, Maca, MYNN 2.5, QNSE, Xinhong, TKE scheme, option 16, University of Washington, and YSU. And just want to mention that besides the 1 kilometer domain, there's actually a parent grid at 1 kilometer, about 500 by 400 points, by 57 vertical levels. And over Colorado domain, domain 2, 1 kilometer domain, it's about 700 by 600 points, and with 57 vertical levels. 4 case studies shown in this talk. Cold air outbreak last year, February 22, 24. If you lived here, you might remember how cold it was. And then case 2 is a typical summer convection case last year, early August 2023. Usually you have afternoon convection here. If you live here, it's kind of pretty regular. You gotta see it. And then the case 3, more quiescent summer conditions, late August last year. And in case, actually 2024 is my typo. Well, last year we had a pretty severe like snowstorm event, kind of rain turned snow overnight. And then the business and schools were shut down for 2 days. If you remember, we lived here. And then on the bottom left panel, the cold air outbreak case, the temperature reached almost minus 25 Celsius, just from Denver International Airport. And then the radar reflectivity for case 2, you have convective storms, to the lee side of the mountains. I'm sure that you live here, you notice this pattern. So this is from case 1 for the cold air outbreak. Upper left panel is the 2-meter temperature of Denver International Airport. And you can notice that initially the model for all of the models did pretty well, cooling at night. But the warming during the daytime is a bit overshooting. And then you have a warm bias after that. And then looking at the wind speed in the upper right panel, the wind speed was a bit too low during the nighttime, but then recover a bit during the daytime. It's a bit noisy, but I think most of the models perform like, in terms of magnitude, they're close to each other, except for the TKE scheme, which had a pretty positive bias after day 1. And then looking at the cumulative error statistics for temperature, lower left panel, you can see that probably the worst performance came from the Bourgeois, Le Carré, and the TKE schemes. It was a bit higher than the other schemes, and the QNSC generally performed like within the pack, except for the last like 12 hours or so, a bit higher. That's the highest, last 6 hours or so. And then the wind speed at 10 meters at the bottom right panel. Again, the Bourgeois, Le Carré, and the TK schemes perform the worst. And generally, the QNSC scheme perform the best compared to others. That's what we expected. Then on to the next case, the summer convection. And on the upper left panel is the stage 4 1-hour precip. And then the other of the other WRF experiments, I'm just presenting the first 4 here because I can't fit everything in the same panel. But in general, the models did pretty well compared to the stage 4 at this time. And then next, the other 4 experiments. Also, the other 4 experiments did pretty well compared to the stage 4. So That's a pretty good performance for the WRF model. And then for the next case, all right, okay. Oh, sorry. This is cumulative. I'm actually still working on case 2. For the cumulative error statistics, looking at the 2-meter temperature and then the 10-meter wind speed and 10-meter wind direction. First, upper middle panel for the 2-meter temperature. I think except for the last few hours or so, I think Q and AC perform pretty well. And the worst comes from the Bourgeois-Lacret and the TKE schemes. They perform the worst compared to the other schemes overall. And then on the bottom left panel of the 10-meter wind speed, and University of Washington PBL scheme perform the worst, fortunately. And the QNSE and the other schemes perform within the similar range in terms of the errors. And then on the bottom right panel of the 10-meter wind direction, I think most of the models perform similarly for the wind direction. Right, and onward to case 3 with the summer question condition during August, and then looking at the 2-meter temperature MAE and the 10-meter wind speed MAE and the 10-meter wind direction MAE. For the 2-meter temperature MAE, again, the TKE scheme and the Bourgeois-Lacret scheme perform the worst. And then the QNSE scheme generally perform within the pack, but it seems like around like 20, see, I think over 21 Zulu, a couple of times they had pretty high MAE compared to the others. For the 10-meter wind speed, for the TKE and the Bourgeois-Lacret, they had a worse performance. And the QNSE had pretty low errors initially, but then the errors picked up after that, and especially about 21 Zulu, it had pretty high errors. And then for the 10-meter wind direction MAE, we have pretty similar performance across the board. And then looking at the last case, I don't have time to show the precip pattern, but they all look pretty similar. So for the 2-meter temperature MAE, the top middle panel, the lowest came from Xinhong, a lot lower than others. And then the next lowest would be the QNSE. And for the 10-meter wind speed MAE, the Bourgeois-Lacret had higher MAE starting from after day 1. And then the Xinhong had the lowest MAE also after day 1 as well. So kind of like the opposite performance. The Xinhong did pretty well in this case, better than in others. And then for the 10-meter wind direction MAE, except for Xinhong did better than the others. I mean, every experiment has pretty similar performance. Right. So summary: the Bourgeois-Lacret PBL scheme, the TKE scheme, they perform poorly for the cold air outbreak case, and then the 2-meter temperature performed pretty poorly for other cases as well. All of the PBL schemes perform pretty well for the precipitating cases. And then the QNSE scheme performed well for the 10-meter wind speed during stable conditions. For active weather cases, QNSE performed well for all near surface variables compared to other schemes, except for certain times. We may consider using this QNSE for the 5-year analysis, but we need independent observations to validate the reanalysis for selected periods. And this is the work that's ongoing. Thank you.
Questions, Wayne?
So how did you initialize the surface? The surface conditions, soil conditions, et cetera, exert a very strong control on the boundary layer behavior, not so much in your winter cases, but especially in the summer cases. And each PBL and surface layer scheme combination has a different preferred climate. So if you use the same soil conditions for each of the runs, you may get different answers, but they may not have to do with the performance of that scheme in a run where it was allowed to reach its own climate.
I use her reanalysis. I mean, her analysis, not reanalysis. Her analysis with the initial boundary conditions, also with the LSM variables, and it is, you know, I think you made a good point. But it is difficult to do all these like different combinations that would like fit the optimal conditions with the physics. I mean, that's one reason that we're using the nudging, because they'll, you know, it's not the, you know, the best way to do this, but we'll correct the errors.
Hi, are you able to comment a little bit about some of the mean absolute error related to the wind direction?
Okay.
You know, in some of those plots, it seems that the mean absolute error was almost 90 degrees out of phase for most of the model PBL options. And for quiescent conditions, that's not all that surprising because it's light winds and the winds are all over the place. But for the winter storm case in particular, that seems like not the greatest model performance.
Actually, those kind of errors are typical what we see in WRF. They can be pretty high, and perhaps one reason is that we have you know, observations over complex terrain where maybe you have just the, you know, the different slope angles are not correct, so you can have pretty large errors. But I mean, those errors, you know, I've been doing verification for a long time before, and they're within the bounds of what we see normally. I'm sure other people in the audience have done, you know, same thing too, probably seen similar kind of magnitude.
Any other questions? Okay, thank you, William.
Thank you.
The next talk is going to be Haley Shen at NSF NCAR again, and she'll be talking about uncertainty near surface meteorological parameters over South Korea with planetary boundary layer and urban canopy processes in WRF.
Yes, thank you. And I slightly shortened our title. And this is a collaborated work with Yonsei University and National Institute of Environmental Research in South Korea. Okay, so let me provide with some background why we are doing this research. So the National Institute of Environmental Research is an agency in South Korea, and they provide operational air quality forecasts. And for meteorological input to their air quality forecast, they use the WRF model forced by global forecast. And some research studies reported biases in air quality forecasting and suggested the prediction of low-level meteorological parameters in their NWP model as a potential contributor. So in this study, we first wanted to identify then what are the systematic biases in their model, and also wanted to quantify uncertainties associated with boundary layer and urban canopy processes, which are important in the prediction of low levels. And we finally selected a boundary layer and urban canopy processes combination that works best for this domain. So this is the WRF model configuration we used, and we tried to make it as consistently as possible with this operational NIER and WRP model. So the innermost domain, we use 4-kilometer grid spacing covering the South Korea, you can see from bottom left plot. And for physics parameterization, especially for boundary layer and urban canopy processes, is currently using Yonsei University PBL without any explicit urban canopy model. So using this, we call this pseudo NIER and WP model. We first identify systematic biases in the contour models that are focusing on low-level prediction. So this is a case example of linear cycle of 2-meter temperature. So shown on the left side is the modeled and then observed time series of 2-meter air temperature. This is averages over all ASOS locations. So you can see that the model, the blue Leg 1 shows these cold biases near the time of daily maximum temperatures and also large warm biases at nighttime. So the left one, this is just station averages, and the right one, you can see actually the biases of individual stations. So this is the box plot of showing this distribution of biases, and you can see that this daytime cold bias and the nighttime warm biases are found at the majority of the Aerosols stations, more than 75 or so stations. So it's consistent with these station means. So next plot, we compared horizontal distribution of this modeled 2-meter temperature with Aerosols observations. So the left side, we have the distribution at daytime, which is likely under unstable conditions, and the right side is the at nighttime, which is likely under stable conditions. And the middle panel, you can see this cross scatter plots comparing observation and model, again confirming the dominance of cold biases in daytime and then warm biases at nighttime. And if you look at the statistical scores at the top left of each scatter plot, you can see that this control setup shows better prediction skills in terms of correlation, bias, and root mean square error in daytime compared to nighttime prediction. So the previous two plots are for a single case, and now we applied it for different cases under different weather conditions. And you can confirm that, again, these daytime cold biases and nighttime warm biases are found in the majority of cases that we selected on the various weather conditions. So we can say that these are the not case specific, but these are the systematic biases in their control model setup has. So this was for 2-meter temperature, and then now we are going to 10-meter wind speed. Again, this is a case example. And the left plot, you can see that this control setup has the model shows excessive wind throughout the Dynar cycle, actually the entire Dynar cycle. And then if you look at this right plot, this excessive wind biases are almost in at all stations, and the biases can be as large like as 10 meter per sec. So it's really huge biases here. And this is the spatial variability. Again, the daytime on the left side was daytime, and then right, okay, that's good, yeah. And the nighttime on the right side, and again, the high biases. And especially if you look at this 2D map, you can see that the high wind biases are more profound, especially more profound along the major mountain range that are highlighted with these circle markers. And for the prediction skill scores, this control setup especially shows worse prediction skills in the prediction of surface wind compared to temperature. So yeah, again, this overestimation throughout the Dynar cycle was found at various weather conditions and then various cases. So until now, we identified the systematic biases that their control model setup has for low-level temperature and wind has. So our next question is to what degree can we improve this simulation by changing boundary layer and urban canopy processes, which are important in the prediction of low levels. So we quantified uncertainties associated with these two processes in the model using the physics ensembles. So these are so we configured physics ensemble consisting of 7 different boundary layer scheme and 4 different urban canopy processes, including no UCM, which is the current control model setup. So we configured this ensemble consisting of these 22 different combination of boundary layer and urban canopy model. And this is the result of ensemble simulation. And this is case composite. So we composite all the cases, and this is for 2-meter air temperature. The black dotted one is the Aerosols observation, and black solid line, you can see contour that I already showed you earlier, and the gray one, this ensemble mean. And again, the ensemble mean also shows this daytime cold bias and the nighttime warm bias. And you can see this spread from this PBR and UCM ensemble is much smaller than our model error, which means that this PBR and uncertainty in these two processes are not sufficient to represent this model error. One good news is that at least for daytime temperature, you can see the maximum, ensemble maximum is close to observation. So maybe we can we can reduce some daytime biases by carefully selecting boundary layer and urban canopy processes. However, for nighttime warm bias, you can see even the ensemble minimum is like the 0.5 degree warmer than observations. This means that we need additional effort beyond just changing the boundary layer and urban canopy processes to remove this or fix these warm biases in daytime. So this is for 2 meter temperature. Yeah, 10 meter wind speed. You can see, again, even the case composite and then ensembles, you can see overestimations throughout the day, and the error is much larger than spread, and then none of the PBR UCM combination can improve these simulations. So finally, we selected the best PBR and UCM combination to be used for this forecasting model of South Korea. So I'm not going to into too much details, but the matrix we used is Taylor diagram. So the left one is for 2 meter temperature, and then right one is for 10 meter wind speed. And this is Taylor diagram for temporal variability, I mean linear variation. And in this plot, the different colors means the different boundary layer scheme, and different shapes means the different urban canopy model. So one thing I want to point out is that you can see the 10 meter wind speed, it shows larger sensitivity to PBR UCM combination compared to temperature. And also comparing the impact of urban canopy model, which means different symbols versus boundary layer, different colors, you can see larger impact by urban canopy model. So this was for temporal variability. The next one is the spatial variability, the horizontal distribution and daytime. So we found a similar tendency, the larger sensitivity in wind predictions and larger impact by urban canopy model. And this is the last one that now is the spatial variability and nighttime. And yeah, so based on these three Taylor diagram analysis, so there was no single PBL UCM combination that performs best for all this spatial variability, daytime, nighttime, and temporal variability, unfortunately. So we kind of subjectively selected the best combination overall. So we decide to keep the boundary layer scheme, which is the control setup, the YS PBL, but overall this built-in effect parameterization UCM shows overall good the improved performance. So we decide to use this best combination for our next project years. So in summary, we identified systematic biases in the prediction of low-level temperature and wind over South Korea. And we quantified uncertainties associated with boundary layer and urban canopy processes using the PBL UCM physics ensemble. And for nighttime 2 meter temperature bias and the excessive 10 meter wind speed bias, we found that even this 22-member PBR UCM ensemble is still apart from observations. So this result indicated that we need additional effort beyond the selection of the best PBL UCM ensemble is needed. So for example, we actually need to look at the actual boundary layer and urban canopy processes or other part for algorithm development. Finally, we selected the best combination, and we will use this combination to further algorithm development in the next coming years. And one of the idea we have is to optimize uncertain and adjustable parameters in the selected boundary layer and UCM schemes. And we also started investigating other aspects of surface physics, including land parameters and subgrid scale topographic wind scheme to further improve the prediction in the South Korea domain. So this is all I have for today, and thank you.
Are there any questions for Haley?
It looked like some of your worst errors were over the mountains. Do you care?
Oh yeah, we care. So yeah, so that's one of the, because actually, we care. And then so that's one of the reasons that we are starting to looking at this topographic scheme to see if it's impact. And especially, so not for air quality forecast, but for overall the NWP over South Korea, that excessive wind over orography is really related to orographic precipitation over South Korea. So we care a lot.
But not for air quality. Yeah. Another question. I forgot what my other question was.
Sorry, my answer was too long. Please email me when you remember.
I think we have a question online.
Yes. So did you test other PBL schemes more than TIN and WRF for the same cases?
Oh, you mean that those outside of WRF? Or you mean other PBL scheme? Do you mean that the PBL
options above 10, you
10?
Yeah, option 1, 2, 3.
Let me see. I think I can see if I tested from. No, I don't have 10 in my list. So I selected, so this is not all available scheme in the WRF model. I think we only selected 2/3 of them, and we, I think, selected that has been used or tested over South Korea before, and including some new options that's recently implemented and have shown in kilometer resolutions, but I haven't tested over 10. But we'll think, we'll test that. It's easier for us to add one more. But I think it's likely systematic biases, so I don't think the boundary layer options could slightly elevate the bias, but I think it's beyond the PBL and UCM.
Hey, thank you.
Thank you.
And our last talk is John Pline at the US EPA, and he's going to talk about urban modeling, both WRF and CMAC coupled modeling for New York City.
Is that it? Excuse me. Thank you, Rob. So I'm talking about a new high resolution urban coupled meteorology and air quality model, WRF and CMAC. And I'd like to acknowledge my co-authors, Jerry Herway, Roger Turnow, David Wong, and Lee May Ram. Okay. So why do we need urban modeling? Well, for air pollution. Human exposure to air pollution is especially acute in urban areas, obviously, where the highest emissions are for commercial cooking and vehicles and other sources. Also, the high concentrations tend to accumulate within the building canopies, where ventilation is limited. And many urban neighborhoods have large minority populations, leading to EJ concerns. That's environmental justice, big deal at EPA lately. Currently, there's a gap in our air quality modeling between the very local, the dispersion models such as AirMod, and the regional models such as WRF CMAC. So we've been, excuse me, we've been working on a new multi-layer urban building canopy model in WRF. This model is built into the ACM2 PBL scheme and the PX land surface model, which is commonly used for air quality applications, particularly with CMAC. So we call that UACM. The formulations are quite similar to the BEP and the BEM based on Masson and Martilli, but they're simpler. We've simplified it somewhat to make it much more computationally fast. It was originally developed in collaboration with Hong Kong University of Science and Technology, Professor Jimmy Fung and his students. And this was applied to Hong Kong at 1 kilometer grid resolution, and it's published in these papers. Lately, we've been doing further development and application to New York City at a finer mesh at 444 meters. And I know we're getting into the gray zone, but we haven't really dealt with that too much other than to look for where it's oscillating. Where things are oscillating, we like, oh, we've gone too far, but it looks like it's behaving fairly well. And then we do an online coupling to the urban modified CMAC. And on the right here, I'm showing, that's the right, yeah, that's the right. This is the building area fraction. This is the domain we're using at 444 meters over New York City. This is the grid average building area fraction, and lower one is the building height. They're just average to the grid cell. Recently, we've done some further advances beyond what was published a couple of years ago. That model assumed a single dominant street direction for the street canyon wind and energy calculations for each grid cell. We've added a second street direction, assuming that two-direction street grids are common in most cities. The building parameters that we use in this case are the grid average building heights, the plan area. This is derived from a database we got from New York City called Pluto. And then we got the street data, and we derived the block dimensions and street orientations from the street data, and that's shown on the right here. This is a sort of zoom in for Manhattan and Brooklyn and Queens. That's showing all the streets that are in the street database, and it's showing the average building height on the grid cells. One of the most obvious effects on the meteorology is the urban heat island effect at night. The base model's on the left. This is at 6 a.m. local time on June 16th. So it's a clear night, and the urban model doesn't get as cold over the urban area. And you can see all that orange area is pretty much where the most built up parts of New York City are into New Jersey. Meteorology evaluation is quite challenging. There's very few measurements at street level in a city. And most mesonet sites are on tops of buildings. METAR sites tend to be in parks and airports. New York State has a very nice mesonet network. They're very well described with pictures and everything, but there's only one in each borough. So we looked at the one in Manhattan particularly. Other mesonet and micronets, we look at their data, we try to evaluate, but a lot of it's less reliable and quite intermittent. Here's an example of a mesonet site in Jackson Heights in Queens. This is comparing the urban model to the base. So, and you see what you expect, that for the 2 meter temperature, which is on the top here, the black is the observation, the red is the urban model, and blue is the base. You see the daytime measurements are not too bad, but at night, the base model gets way too cold in some of these. Sure, oh, there's a thing, right? Oh yeah, I like that. Hard to control this thing. All right, yeah. So I mean, like these clear nights when we're in a warming trend, the base model is way too cold, and the urban model is agreeing quite well with the observations. This is the 10 meter winds at the bottom. The urban model has reduced the winds because the buildings get in the way, and closer to the observation, still a little bit high bias in this case. Here's LaGuardia Airport, which is also in Queens, not amongst the buildings, obviously, but there's a lot of urban area around it. And this is comparing to BEM. And in this case, oops, well done again. Yeah, here we go. In this case, you see a somewhat similar thing when we compare to the base model. The BEM tends to be too cold on some of these clear nights. Not as bad as the base model, but anyway, the urban, our UACM is getting better results compared to the observations at the low temperatures. And then the biggest difference is in the winds. And down here you can see that the UACM in red is comparing quite well with the observations in black, but the BEM is just way too low. And this is an issue that I don't know how many others have seen this, but it tends to come from the way they do the building momentum drag for the two directions, and they average the two together. So if you figure if you have a two-dimensional grid, two-dimensional street canyon, and you block the winds going against the buildings, and then you do it the other direction, you block the winds in both directions, and you don't have much wind left. What we do is we do them individually. We say we compute the wind stress for one street direction, we compute the wind stress for the other street direction, but we don't average them together. We run the wind model in the PBL for each one independently, and then we average the resulting winds, the U and V component. Seems to come out with a more realistic result. That's one of the biggest difference from BEM. Here's the Mesonet site at Manhattan, and you see that this is actually where the site is on top of this building. It's hard to control this thing. All right, where you see the red flag. They're really good at describing their data. And this is just showing the vertical profile of wind speed at this location and for a particular evening. The urban model clearly has a much lower wind speed within the urban canopy. The base model shows the typical logarithmic profile, but the urban model is reduced. And then, so what we did then in this case, we found the level in the model that represents the height of the sensor. For wind speed, we assume it's like 10 meters above the roof. And we compared the base model and the urban model. They're both a bit high in this case, but the urban model is closer to the observations in green. And for the winds, it turns out to be level 7 because it's 2 meters above the roof. And again, you're seeing that the base model gets too cold. Oops. At some of these nights, and the urban model is doing better. So we get into air quality. We've coupled it with CMAC, so it's running online coupled. And this is at 444 meters. And the left panel here is showing the building height. This is I showed before, but this is the building height. And you can see what New York City looks like with Manhattan there in the middle. There's two areas in Manhattan that have the highest buildings in kind of midtown and then downtown. And the reason I'm showing that is because the PM 2.5 concentration in the middle panel, and this is for a particularly, a very light wind speed case, clear light wind speed case, you get this accumulation of concentrations in the high building areas. So you see in this location here, in the midtown and then downtown. I know you have no map, but that's what it is. It corresponds very well to where the highest buildings are over here. And then the base model just doesn't show the building effect at all because it doesn't have the building effect. So we modify the CMAC in a couple of ways. One, to account for the reduced air volume within the building canopy, which then changes as you go above the roof. And then the biggest effect is adding dry deposition to the walls and the roof. We had to develop a new algorithm for doing that, and that's very important, actually. Let's move it here. I'll move it. I'm pointing it the wrong way. Not getting it to move. But hey,
Yes, it's the top button.
huh? The top button goes backwards, right? But neither of them are working. Yeah, this should advance it, right? But you know, wait. You advance my slides? Could be. I don't have another one on me. That's the, yeah, that's the, I want to advance the slide. Right, go ahead and push it. It doesn't do anything. That's the issue. Oh, wait, okay. All right, sorry about that. So air quality evaluation also challenging in this kind of scale. But we focus on PM 2.5 because that tends to be the worst local issue in cities. And so we look at the AQS sites, which is an urban net, I mean, an EPA network, and there's some sites, a few hourly, and most of them are daily. And then there's a network from New York City called CAS, and they're really street level, which is very nice. But the hourly data for this period in 2018, there was only 2 sites that had a complete data set, and one's in northern Manhattan and at a bus stop, which isn't the best, and another one was in Queens at Queens College. And there's a really nice one in lower Manhattan, but they only had 2 days. So I've got to model another year to get a lot more data, which I'm in the process of doing. Anyway, here's the 2-week average from the New York City network, and on the left is the bias, and so the model tends to be biased high over Manhattan. So I think I'm going like this. Okay. Oh, yeah, there we go. See how the over Manhattan is the highest biases. The rest of the area, like in Brooklyn and Queens, very little bias. And then on the right is just showing that the urban model has a reduced bias, all the blue and purple, compared to the base model in most of the sites, 2/3 of the sites. Here's one of the few hourly sites that had good data. This is at Queens College, not a real dense urban area. I mean, around it is, but you know, this is a college campus. But you see the model is producing a pretty good following of the observation. The observations are green and the model is red. This is for the whole period, like almost 4 months. So it's following the data fairly well. Here's another one it's an AQS site, hourly AQS site. This one's in Manhattan, East Village. It's on top of a school. The model tends to be a little high, maybe because the observations are on the roof and the model I'm using is the bottom. But anyway, again, it's following the observations quite well. So in conclusion, the new urban model represents the urban heat island at night quite well, much better than the base model and seemingly better than BEM as well. The winds are reduced in the building canopy, but not nearly as low as the BEM or BEP. The PM 2.5 generally follows the observations in the data we have, in the hourly data we have, which is not that much. But it tends to be biased high in Manhattan. The nighttime concentrations are much reduced. Oops. I wanted to just show quickly on this diurnal plot. These are the distributions over the 4-month period diurnally, or by hour of the day. The black ones are the observations from all the AQS sites. The red one is the urban model and the blue one is a base model. And one thing you see is the base model tends to be way over predicting at night because without the urban parameterization, it gets way too stable. Emissions accumulate, the concentrations get way too high. The urban model doesn't do that. The stability is fairly neutral day and night because of the effects of the buildings. And although we do have a high bias in the daytime, because it doesn't get as convectively unstable in the daytime as the base model does. Anyway, so we plan to do more modeling in 2023. in New York City, maybe Chicago. We'll see. Anyway, thanks.
We have time for one question.
Hi, really interesting work and, really interesting results. I see you've mentioned the New York State Mesonet. Have you looked at all at some of the profiler data that they have down in New York City, or do you think there's value in using some of that information for model validation going forward?
Yeah, we have looked at that. And I had some slides on that actually, but the resolution, it doesn't really get down to the building canopy. First of all, the instruments are on the roof of the buildings, so you don't really get anything below the roof. And then I think the first data is 50 meters or something above that. So yeah, you can see some effects of the building data, and it's generally an improvement, but it doesn't tell you a whole lot because it's not getting low enough. Getting into the building canopy is the tricky part. People don't tend to put, anemometers and next to the street. They do put PM 2.5 monitors though, so that's very nice. Oh, anything else? No.
Hey, thanks, everybody. Give all the presenters a hand.
Okay, I think we should try to get started. We are, if we get too slow, we're potentially running into lunchtime and nobody wants to do that. So I will use the timer for my own information here. But when you get to about 12 minutes, I will stand up and look increasingly impatient. And so hopefully we'll try to stick to time. And our first speaker, Chen, I think. So go. Like we need to backtrack a bit there. Okay, very good. Go for it.
Okay. Good morning, everyone. My name is Wanzheng Wu. I'm from the Asia Pacific Typhoon Collaborative Research Center and Shanghai Typhoon Institute. I'm excited to be here attending WRF MPAS workshop today. And for years, we have focused more on the subject of hail prediction. And we closely follow any advancements in hail parameterization in the microphysics schemes. And earlier this year, we were thrilled to see the release of a new Thompson scheme that includes the hail prediction capabilities. So today I will present our preliminary work on exploring the different hail microphysics schemes in a real case hailstorm simulation. So I'll skip the simple outline of my presentation because I only have like 15 minutes. And I think hail microphysics scheme is essential to simulate the hail initiation, growth, sedimentation, and the melting processes, as well as their interaction with the other hydrometeor species and the environment. So if we look at the bigger picture, we notice that the storm simulation is also crucial to create a favorable environment with like intense updraft, moisture transport, thermodynamic instability, or low level wind shear for hail to grow at the right place and time. So considering all the uncertainties in simulating hailstorms and hail, we are still facing numerous challenges in predicting the timing, intensity, and the spatial distribution of hail events. So today we are going to review a hailstorm that occurred on September 4th, 2020 in the Shandong province. And the storm was initiated and intensified between like 4 p.m. and midnight local time. We have hail photos on the road in Rizal City show that the diameter was greater than 2 centimeters. And this study has two main objectives. First, we are going to evaluate the performance of the new scheme in simulating hailstorm and the predicting hail, and to understand the variations in hail simulations across 4 different microphysics schemes. And second, we are also interested in any potential feedbacks of the hail-related microphysical processes to the storm development, such as the storm intensity, latent heating, downdraft, and cold pool intensity. And finally, we will compare the predicted hail sizes with the observation data. So here is our model domain and setup. We used WRF model version. See? I think I pressed the wrong button. Okay. WRF model version 4.5.2, and we have a fixed resolution of 1 kilogram grid embedded within a 3 kilometer grid covering the East China. And the initial time was 00 UTC on the 4th, and with model outputs generated every 10 minutes for us to study the interactions between hailstorm and the hail microphysical processes. And we have the same physics, but except for the different microphysics. We used the original aerosol aware Thompson and the WRF double moment 7th class schemes for the single moment hail simulations. And we used the National Taiwan University and the new Thompson schemes for multi-moment hail simulations. So we have 4 experiments for 4 schemes. The table summarizes the variations of hail parameterization of the 4 schemes. We have the single moment schemes shaded in blue and the multi-moment schemes in red. And the 4 schemes predict different species with different bulk densities, particle size distribution, and the prognostic variables. So look at those differences on the table and many more behind the table. I want to say that I love those schemes, but it's a real pain. So for the hail size and the reflectivities we used in this study, we calculated the maximum estimated hail size of the real storm from radar reflectivity by the WIT 1999 method. And we used the NWP diagnostic module of the WRF model to calculate the maximum hail size for the simulations. And another thing we did was we borrowed the reflectivity module from the spectral beam microphysics for the NWT because as they share the similar hydrometeor variables. So results. First, the reflectivities. We have the observation and simulation results. And we can see that the simulation results are different from the observation in many places. So in the simulation, the convection initiated early and intensified rapidly. And those convective cells are developed around the corner of the Yellow Sea. And they organized into a line parallel to the coastline. This differs from the actual storm that which was more perpendicular to the coastline. So maximum storm intensity, we found the new scheme performs comparably to other schemes, but we could also see some large variabilities in like a minima 2-meter temperature, rain intensity, and the hail precipitation in size. And especially the hail precipitation and the maximum size among the 4 experiments are quite distinguished. And we can see that the WDM7 scheme produced the highest amount of hail precipitation, and the new scheme generated almost none. But for those markers are the maximum hail size. We can see that the 3 schemes predicted like hail size around 3 centimeters, and the new schemes predict between 1 to 5 centimeters in a larger variabilities. So here we present the instantaneous cross sections of hail variables at a specific latitude and time to understand to explain the size variations. So on the left, we can see the fourth experiment produced the comparable graupel and the hail mixing ratios in various extents in the storm. And the new scheme produced like at least a mixing ratio below the freezing level, which is consistent to the minimal hail precipitation we saw earlier. And on the right, we have the number concentrations in shaded colors and the median value diameter in dots. And we can see the single moment schemes produce the lower number concentrations, especially in the convective core, than the multi-moment schemes did, resulting in larger particle sizes. And in contrary, the multi-moment schemes produced the large particle sizes in the narrow gaps between the high mixing ratios and or high number concentrations. So we can see this is the major difference between the single moment scheme and the multi-moment schemes. And here we are going to see an interesting coupling effect between the force speed and the melting process below the freezing level. And we have the frequency of the mass-weighted force speed and the mixing ratio from the 4 experiments. And we can see the single moment schemes, they have a positive correlation between the 2 variables. And this means that larger mixing ratios, they are going to fall faster than smaller ones, and thereby reducing the melting rate due to the shorter airborne time. And for the multi-moment scheme, the large mixing ratios, they actually they can fall at a slower speed, so more could be melted before they reach the ground. So this effect can be associated with the gradient of the total graupel and the hail mixing ratios below the freezing level, because we can see that the gradient is lower with the single moment schemes, and they are steeper with the multi-moment schemes. So another important subject is the microphysical feedback to the storm environment. We have on the left, we have the domain summation of latent heat averaged over time. And we can see the NTU scheme and the WDM7 scheme produced a slightly more heating in the mid levels and more cooling in the low levels. And later we identified that this extra cooling was not resulted from the stronger deep convection, but from a slightly greater number of the weak convections. And on the right, we use different percentiles of the 2-meter temperature to evaluate the cold-pool strength. And we found that the NTU scheme produced the lowest temperature by the first quartile and the median value. So we believe that the NTU scheme produced the strongest cold pool, along with the most intense cooling rate and the downdraft in our experiments. So we found that the relationship between the cold pool strength and hail, that this is seems to be somehow like related but not clear. And so therefore we concluded that the hail-related microphysical process, the feedback to the storm environment is not that impressive. So the last thing we do is to compare the predicted hail sizes and the observation. We have the simulation results in the first row, and we have the derived MEHS parameter from the radar reflectivity every other hours in the second row. And we can see a distinct feature between the simulation results and the observation, mostly due to the positional error of the storm simulation. And we can see the new scheme, to our surprise, can predict the scattered feature of hail events with similar like hail size prediction with others. So this is out of our expectation. So to close, from the perspective of hail simulation, we found that the key difference lies in the parameterization of hail number concentration, and which varies significantly, and thus it would affect the hail particle size and the hail-related microphysical processes considerably. And but we noticed that in this specific case, the feedback from hail microphysics to the storm environment is not that impressive. And we found that the new Thompson microphysics schemes performs comparably to other schemes in hailstorm simulation and exhibits unique characteristic in hail simulation. So I think that's it. Thank you for your time.
Excellent timing. We have time for questions. Questions?
Go back to your figure of reflectivity where you show the evolution.
This one?
This one. Yeah, so I mean, it looks like a lot of these schemes are evolving very differently in terms of their storm structure.
Yeah.
How do you kind of take that into account when you compare?
So I think the details yeah, you can say the details are varied differently. And I think they are related to the explicit the amount of different hydrometeor species, because the radar reflectivity are derived from those variables. So, but I think it's kind of usual to see those differences, but the most important thing I want to see is how those differences affect the storm development and the intensification. And in our like the storm maxima storm intensity, you can see the maxima updraft and the minima outgoing long wave radiation. They are kind of similar during the simulation time. So and the structure, if you look at the structure, you see they are kind of similar to be like I said, the parallel to the coastline extending out to the sea. So I think it depends on like which kind of structure we want to focus on.
Thank you.
Sorry if I missed this. Just a practical question. Does the augmentation here to this in the reflectivity diagnostic make it more costly? One of the challenges we have is the expense of even running the reflectivity diagnostic one.
Oh, you mean you are talking about the method, how
Yeah.
to calculate those reflectivities?
Mm-hmm.
Yeah, I try to use those like the here I mentioned. So for the Thompson scheme, they have their reflectivity module.
Which is not cheap to run.
Yeah, and for the WDM7 scheme, actually I checked those refractive module because they are different because they have different like hydrometeor variables, right? So I checked the structure of the code, and I think I found some similarity, but they kind of adjust to the different hydrometeor species. So I'm not the expert of the radar reflectivity, but I believe they are comparable.
They're comparable, so you don't think the runtime for adding in this is going to make it any more expensive than it is now?
And I think it's possible that like the previous question, they could look slightly different. So I try not to be bothered with those differences.
All right, thanks.
Thank you. Our next speaker is Sung-Yu Hong.
Hi, I'm going to talk about the ongoing efforts in devising or development the double moment parallel scheme. this is collaborative efforts of NOAA, PSL, and GSL, also NCAR. It's not a new scheme. It has a long history starting from the 1998 paper, NCAP cloud scheme and WSM, WDM scheme. And in 2018, we devised the idea of in-cloud microphysics, or some of the ice microphysics in GFTL microphysics, which is operational now. So it is WSM scheme was written about 20 years ago, and WDM more than 10 years ago. So that time to develop one release another one. So that strategy take all the advantage of previous developments, also adopt the findings in the literature and the bug fix. Code was entirely rewritten. For computer efficiency, major two components here, and the tentative it is called the UFS double moments, so-called UDM microphysics scheme. So that is in-cloud microphysics, very simple concept in nature. If you see the left, is suddenly less than 100% cloud. Right side is a 98, for example, but the microphysics computation, it assumes that 100% cloudy. It's not physical, so that we set up the idea of in-cloud microphysics based on the observational evidence. So that here, this is the observational evidence, is a cloud fraction, is a function of cloud or content. So that the grid mean state, we treat the advection or sedimentation or PBL mixing treated as a grid mean state. And the other microphysical process treated with in-cloud physics. It is pretty much simple, and because the cloud order and the suppose rate. Suppose 100%, then we have a solid line, and then if we assume the 50% cloud, so it is more condensed in the grid box, so that is enhance the auto conversion rate. Our math very simple, no cloud overlapping like in the IFS model, but yet applies to all the sources synchrotrons. Another concept is sedimentation of a hydrometer, which is a monotonic mass conserving sedimentation. This is the motivation is to add the semi-Lagrangian. It's too expensive in the Eulerian sedimentation with the sub-stepping. So that we developed this semi-Lagrangian scheme, which is, this is different from the conventional semi-Lagrangian. Conventional semi-Lagrangian has iteration to find the departure point. Instead of doing that, suppose this is a raindrop, we had a terminal velocity at the top edge and the bottom edge, and they had a separate forward scheme, and then it can be shrinked. Raindrop volume can be shrunk or expanded, but mass is exactly conserved. Also absolutely stable. And then we further examine this issue in the sedimentation only offline test. Upper is a QR and the bottom is NR every 6 minutes sedimented. So that a bin model on the left and the Eulerian scheme. Eulerian scheme typically has a mass conservation issue, quickly dropping. So that is Euler advection WM6, other scheme work model for additional deficit of mass. So that it was pretty okay in the single moment, but it's an issue in double moment. And surface rainfall for 1 hour, again, is the delta T, 180 seconds, 18 seconds. Beam microphysics produce 18 millimeter. Eulerian scheme is 16 millimeter, still 10% deficit, but the larger delta T, 1 second, is only 1/3 precipitation reaching to the surface. But semi-Lagrangian, irrespective of a time step, is very close to the bin model result. It was first added in the Thompson scheme. Thompson scheme is a candidate for version 17. There is diverse efforts tendency inner loop to prevent the model crash. And then we added this Seymour-Lagrangian scheme I presented, reconfigured the Thompson scheme, and then it's pretty much stable. So that is about to save the 10% against the inner loop. But another issue is aerosol effect, only realistic in the Seymour-Lagrangian sedimentation. This is the figure aerosol effect Thompson scheme, 13 kilometer. Upper right is the water-friendly aerosol, and the upper left is a Seymour-Lagrangian scheme with the MP delta time step 1/52. We have a reduction of precipitation of Southeast United States or Europe, where aerosol is abundant. With the earlier scheme, with the delta T is 50 we don't see any impact over the Southeast United States. And then we tested the 2D idealized square line in the WRF model. Upper is UDM, lower panel is the WRF-6 scheme. You can see that new MPS produces stronger convective activity with a smaller horizontal widths. In terms of a storm structure, is upper as 4 hour and 6 hour. You can see that new MPS produce realistic front to rear, also rear to frontal jet, along with the cold pool near surface and outflow at the top. In the WRF-6, there's some up and down structure. And also testing the 2D idealized square line test, also different area initialization starting from the 100 to 5,000 per cc. We can expect that with the increasing CCN concentration, we have cloud number constant increase. Also, diameter of a cloud droplet is decreased, so regional reproduced. Also, compared to WRF-6, so that NC diameter of a cloud is decreased. Also, raindrop size is increased, which is qualitatively comply with the airborne observation. And then we tested in the weather forecasting model, and the CCN is initialized go-kart aerosol. And then in terms of skill score for medium range forecast, pretty much comparable, global, southern hemisphere, we have a slight increase, and then upper slight degradation after 5 days, and the northern hemisphere, black line is slightly better. Black is a new scheme, but tropics obviously is there's a discernible improvement. In general speaking, hydrometer is P8, Thompson, UDM, and UDM minus P8. We have more of a liquid species and less of ice compared to Thompson scheme. And then, but we have some issue in the hurricane development. Somehow, intensive tropical storm, I think, was considerably suppressed, which it is. And then dotted line is observation, and solid line observation. Dotted line is the Thompson. This is the new scheme. 50 hectopascal difference in the central pressure. How to resolve it? We tackle this issue by examining all other terms. Finally, we identified that is an inconsistency between QR and R due to dynamics, PBL mixing, and retrain the hydrometer from the CPS scheme. So that is in UFS, all the traces, including NR, are mixed in the PBL. So that there could be an inconsistency. So that what I did is just that is a complete sedimentation. We switched the sedimentation and the adjustment of NCNR, just order of computation. Then central pressure dropped by 50 hectopascal. So that is pretty much reasonable following the observation. There is no issue in the WRF model because the WRF model doesn't mix number concentration, but it was an issue in the GFS. And then look at the number concentration, global distribution, or upper right is the CCN and the number concentration of a cloud and the raindrops. We realize there's something, it's hard to evaluate, but simply too much number concentration of raindrops. And then examine the diameter, mean diameter cloud drop is 8 micrometer, and the raindrop is 0.5 millimeter looks reasonable, but we realize that new scheme reserve the drizzle as a rain category looks reasonable. But yes, aerosol effect, we tested it by limiting the minimum CCN number. So that is somehow it has a very strong sensitivity to the aerosol number below smaller than 100 per cc. So that is, for example, with this CCN minimum down to 20 per cc, hurricane did not was not developed. So that we are looking into how to interpret or how to scientifically convinced. So the scheme is under development. In terms of world clock time, is compared to GFL microphysics, Thompson micro scheme world clock time increased by 11.4%, and the new scheme is 4.8% increased. New scheme has one additional parametric variable, which means that there are more number of computation in the microphysics, but it's very efficient. Finally, new scheme or UDM, whatever on the development. This is the to-do list, for example, for the prognostic ice number particle, if possible. And then prevent coast UFS protocol, public domains, maybe later this year. That's all I want to say. Thanks.
Questions? I'll ask a question. What do you think the PBL scheme should be doing with these variables?
Yeah, that's a real question. Actually, in the GFS model, all the traces are mixed in the PBL. And then in the WRF model, doesn't mix any traces, and any number concentration, only mix cloud water and cloud ice. I think pretty much is open questions. I have only one literature from the PNNL. They argue that number concentration should be mixed by PBL.
Actually, the MYNN does actually update the tracers as well. Not all of them, just the ones specific to Thompson.
Yeah.
So I don't think we've seen, well, I haven't seen a hurricane sensitivity to that though. Yeah, kind of puzzling to me.
Other questions? Do we have it online? Okay, I guess we'll move on. Anders Jensen is up.
Okay, so I'm going to be talking about some recent changes to the Thompson microphysics, in particular our effort to organize the scheme into one submodule called the Thompson-Eidhammer Microphysics Parameterization for Operations, or TEMPO. So this is a pretty big effort between some code managers, myself, and EMC. So why do we need a submodule? Well, the Thompson-Eidhammer microphysics scheme, the original one, it's used in several modeling systems, and divergent development has really persisted across a lot of these modeling systems, from WRF to MPAS, the CM1, and even in the CCPP. So there are too many versions of Thompson microphysics, and we want to bring them together into one development framework. And so that's what the TEMPO submodule does. It's unifying the microphysics development into one repository that has a full commit history for the changes. So it can be used for across many community applications. Now, specifically for our GSL development, we are focused on using this microphysics both for MPAS, for our Rufus version 2 release, as well as in the CCPP for different global applications. So we need to use this microphysics scheme across various die cores at this point. And this unification effort helps us do that. So where does this submodule live? Well, it lives at NCAR. So there's a link to where the submodule is on GitHub. For now, the organization is as follows. There are, the scheme has been broken up into several modules, a parameters file, which defines the model parameters, a utilities file, which has things like the reflectivity calculation subroutines, and the main code, which is just the 1D main microphysics code. There are also different drivers for different models. And for now, we have a driver for MPAS and for the CCPP, which is, those are the two frameworks that we are developing in. But we are working on additional drivers, one being a standalone driver that will just run the microphysics without a dynamical core. That's useful for testing things. And then we are working on a WRF driver so that the scheme can be plugged back into WRF. There's still a big need for using the Thompson in the WRF model, so we do want to support that. And then we have other directories, including a testing directory, which is honestly a little bare at this point, but we don't want to overlook testing. And we have a directory for tables, which we can store some of the smaller lookup tables that are needed. So the schematic just shows how this is coupled to both CCPP and MPAS. Currently, everything that lives in the submodule right now is in green, although for development and testing, the drivers that control the scheme are currently in the submodule. Those could feasibly be moved up to the host modules at some point. But basically, there's two different ways to couple with the CCPP. There's the physics cap that gets you into the microphysics, and that goes into the submodule, which calls a driver, which converts the 3D atmospheric model to the 1D microphysics code and goes into the main 1D code. And with MPAS, there's a driver for the microphysics, which is more of a kind of a hard-coded driver at this point, which gets you into the MPAS driver on the submodule side and down into the 1D code. Now, in terms of the current development status, in trying to bring everything together, we started by merging in the WRF 4.5 changes into the standalone MPAS version of the microphysics. And so this allows us to have the aerosol aware version of the microphysics, as well as the hail aware version that was just discussed 2 talks ago. So the aerosol aware version is considered the old MP28, if you're familiar with the WRF way of naming things. And the hail aware version has the 2-moment dropple with predicted density. That is the old MP38, although this is newly implemented into WRF. Old just means the naming convention. We are trying to get away from using these MP8, MP28, and MP38 naming conventions. So in addition to these changes, we also merged in recent development from going on in CCPP. There's been a lot of development to get Thompson running in global models. So we have that development in, and for now, there are a few remaining differences in the code that we handle with flags. We don't want to just make executive decisions on some of these changes right now. We want to test some of these differences and work to merge the code in the best way possible. So with our MPAS version, this is currently connected to our GSL fork of MPAS. We will hopefully try to work to get this into the authoritative repository. And then the CCPP version, there is a PR submitted to the UFS community repository to hook this up to the official CCPP. So I mentioned that we want to get away from these like different versions and flavors of Thompson, MP8, MP28, MP38. So the sort of the development philosophy is to handle features with name list flags and optional arguments in the code. And so for example, if you're running this in MPAS, you can still just call MP Thompson with this, and you set config Thompson hail aware to be true. Then the driver will look for the additional grapple prognostic variables as optional arguments. So if you don't have those, the scheme will automatically fall back to the original 1 moment grapple. And if you do have it, it will handle those 2 moment with predicted density, those 2 extra variables. Just a note here, the hail aware version does require new lookup tables, and there is functionality to build those. And it does include 2 additional prognostic variables. So it is going to be more expensive because you need to advect those 2 additional prognostic variables around. But there's a lot of benefit to having the predicted grapple density. Not only can you use it for hail prediction, as we saw, you can also use it to predict high density ice during wintertime storms. So things like ice pellets can be used with this scheme as well. So we're doing a lot of testing with the tempo submodule. As Joe mentioned yesterday, we have set up our own CONUS run that we're running 4 times a day. We are also getting involved in the HFIP project with this submodule. So there's a lot of talk about hurricanes and convection. We don't want to forget about wintertime. It's like 6 months away, and it will be back to winter finally, and it won't be 100 degrees every day. So we are also testing this submodule in wintertime cases. So we're looking at an atmospheric river event from last February. And again, we're testing using both the CCPP implementation and the MPAS implementation. So the case that we're looking at involved a low pressure system off the coast of California. If you look at the figure on the right, the red contours are the mean sea level pressure. You can see the low pressure system off the coast of California associated with a large area of precipitation shown by the reflectivity. This low pressure was slowly moving. It kind of jaunted southward over the course of a couple of days. But it was an interesting case. It produced about 40 inches of snow across Southern California, which is pretty rare. So again, we're testing the tempo microphysics in the CCPP implementation and the MPAS implementation. Now, at this point, our testing framework is the version that we're running in MPAS is very different from the version we were running in CCPP. There's differences in the domain setup and the other physics. So we're not using this testing to say anything about the differences in the dynamical cores. When we run this, we're just doing a simple benchmark of the microphysics and making sure it works and kind of passes the eyeball test in both of these frameworks. So our FV3 domain, we have a pretty big 3-kilometer domain. This is actually a nested domain inside of a global run that we're using for our CCPP or FV3 test. And because this was a slowly moving system, and because we're kind of lazy, we just cut out a small circle over California just to have kind of a simple look at this test case in MPAS. Again, with a 3-kilometer grid spacing. So obviously, in terms of wintertime events, atmospheric rivers, we are very interested in being able to predict the higher precipitation amounts that can occur with some of these events. And so I will show just some, again, just kind of some eyeball tests of this submodule as it's run in MPAS and our CCPP framework, but using FV3. So on the left, this is the 24-hour precip from the stage 4 observations. see lots of precip across Southern California and in the Sierra Nevadas. And our MPAS run, control run being just the aerosol aware microphysics is shown in the center. And, you know, for the most part, MPAS, this run, we're capturing the high precipitation amounts across Southern California. Definitely some under prediction in the central California mountains, but this is something that we're looking at. And in addition to looking at some of this precipitation verification, we're in the process of doing some further verification for these cases. So the figure on the right shows just the normalized distribution of precip in our arbitrary magenta domain. So just how are we doing in terms of the distribution of precipitation across California? And this is for MPAS for our control run, which is the aerosol aware microphysics and the hail aware. And they both perform pretty similarly. They both get the relative distribution of precipitation up to about 8 inches of liquid, which is, you know, not bad for our first cut using MPAS on this. Again, when we run this with CCPP, at this point, it passes the eyeball test. There's maybe slightly less precipitation across the Southern California mountains, but again, we're not in the position to compare MPAS to CCPP at this point. And the distributions of 3 of the flavors of the microphysics are shown on the right. So we have the control, the hail aware, and the non-aerosol aware, just benchmarking how these perform and how they run as hooked up to the CCPP. So, yeah, in summary, we have this new tempo submodule. We've developed it to unify the microphysics across various operational applications. We want to unify across models. We want this to be used for research purposes as well. There's a lot of work in progress. So we're still working on things like documentation, automated testing. We're still refactoring and renaming things and incorporating new development. So it's a work in progress, but we want this to be a community application. We want community feedback. And so my advice to you is create a fork and have fun. So thank you.
Questions? I have a question. Oh.
And it's just a discrepancy in the Sierra Mountains. I think it's just the fact that you're using a 3 kilometer with smooth terrain that's probably not getting you. Is there any way to sort of estimate stage 4, how it sort of back out maybe what it would be more like without that?
Yeah, I mean,
it's hard to do. I know.
It's hard to do. I think, yeah, I mean, terrain is an issue. It's also kind of a cutoff low. So positioning, timing, and location is also an issue. How quickly it progresses off and how far it is off the coast and stuff. So there's a lot of things we should look at for this case.
Actually, my question too.
Okay.
I actually have questions about the Aerosol over Thompson, Hail Thompson scheme. So I'm just curious because this scheme, I noticed that it has new aerosol species, and I wonder, would you like action between the different aerosol species with the hail in the future? Like because we noticed that there's also some paper discussing like how the aerosol affects the hail in the growth processes, or like the density, because you also have the varied density from time. So I'm just wondering.
Yeah, I mean, that's a good question in terms of like the hail. You're talking about like the scavenging of precipitation or the growth processes. Mm-hmm. Yeah, I mean, we definitely have it on our list of things to do to improve how we deal with the aerosols in terms of both the water friendly and the ice friendly, and how it affects not only the growth processes, but how the scavenging is occurring as well.
Please speak directly into the mic.
Yeah, and we can talk more offline. So thank you.
Thanks. So next speaker is George Grell.
All right, so everything I'm presenting here is very recently created. We just kind of swapped out the GF scheme with something new, which is what we're currently using in the Rufus version 1. That was very easy to do. We did not touch very much the GF driver for this kind of stuff. That's actually, it was written in a very nice way, so it made it very easy to change. Oh. Have that figured out. So I'll tell you first what's new since WRF version 3.6 and what we are currently using in MPAS at GSL. And then a little bit on ongoing development and research applications with GF, and also what we now call a community convective cloud parameterization. And I just have one slide on that. I just can't go into detail on all of this stuff. What's new, for one, we have now PDFs that describe the vertical mass flux distribution, which is meant to represent the average of deep convective plumes, and also for congestors and for shallow convection. And the key there is to determine what the level of, where the level of the maximum vertical mass flux is. That seems to be easy for deep and shallow. It does not seem to be that easy for congestors convection, and I'll show you a picture from that too. So there's 3 PDFs, beta functions that are used for this. Cloud water retrainment is now proportional to mass retrainment and in-cloud cloud water ice mixing ratio. We have a routine that does below cloud base evaporation. We keep that optional. It's kind of, we already are kind of on the cool side for, so we don't use it for deep convection. Momentum tendencies are passed on. This was a deficit in MPAS before. They were calculated, but they weren't passed on. Change subsidence terms for cloud water ice, and that's also for tracers to avoid negative mixing ratios. So we're using an FCT routine there. But it turns out we really only need the upstream part of it. It's actually gives smoother and better results than using the whole FCT approach. We changed the scale awareness. This was focused on Rufus version 1, which is supposedly what will possibly get implemented over the next year. But some of that will be similar for MPAS, and I'll have a slide on that too. Mixed phase physics, wet scavenging is included, not aqueous phase chemistry or gas phase scavenging yet. Now, the gas phase scavenging would probably be easy. Gas phase chemistry is a different story. The liquid aqueous phase chemistry. GF was GPU enabled and tested with a good speed up. However, we made a few changes with this version 1 implementation. And we're not experts on GPU, so we'll probably have to go a little bit over it again and make sure we didn't destroy anything there. Testing the PDF approach. This just shows a comparison between the model in a single column model approach using TWP ice data on the left side and a couple of different radar observations on the right side. And you can see that for the deep convection, it agrees pretty well with the location of the observed data. And that's the same for shallow convection, which usually is at cloud base or just above cloud base. But different for congestors, it's pretty difficult to determine where that maximum there should be. And we hope maybe at some point we can get a handle on that with machine learning. Scale awareness tests. Usually you see high biases or the high thresholds for convection allowing modeling when running without convection parameterization. And then most scale aware parameterizations just use a scaling approach for the tendencies. Even though that's pretty neat numerical, see the Arakawa papers, but it has significant physical shortcomings. And that is because, for example, if you have no explicit scheme active yet, say in the tropics or Southeast US, and the convection scheme says, okay, we're getting a big storm here, and then you scale that by a factor of 10, that's just physical nonsense. But that's the way the scaling works. So what we're doing is we only apply scale-away scaling when the microphysics scheme is not active anywhere between cloud base and cloud top. And there's no reason to scale it. Now you introduce another error, of course, because usually the impacts of the convective parameterization would be, in this case, over more than just one grid point. So it's a question, which one is a better error to take in that case? We disabled congestus convection. We only, it's enough to have one in there, one type of convection, but slightly decreased the characteristic cloud size for deep convection. This is something that usually goes automatically, used to go automatically in MPAS. And we do include radar reflectivity calculations from GF. We do not allow to, we did not for Rufus version 1, call any GF if the M1 and shadow convection was active. That's also something that we don't use for MPAS. This is just one example that Jacob Carley showed for the improvement in the scores. And you know, if you see the blue line here, you significantly decrease the bias and you don't change the CSI score much. But the problem is for storm scale metrics, that's just not all you want, because what you're doing at the same time, you decrease the probability of detection from the severe weather events. So storm scale forecasters usually prefer over forecasting rather than under forecasting. Oh, and this is an example of the real-time runs at GSL. I was going to update that with the current forecast. Unfortunately, the last 2 days, computational issues, our HPC system wasn't cooperating. So anyway, whoops, no GF in this case, with GF here. Differences are fairly small. With GF, you have less intensity usually, which is what we expected. Okay, a little bit on development and research. One project is to use AI and ML to train the closures used in the convective parameterization. We have 4 different closures, type of closure: stability closure, low-level vertical velocity, integrated vertical advection of moisture, and another stability closure more like ECMWF. And what we're trying to do is we're trying to use a least square fit and machine learning approach to improve on the uniform average. Right now, we're just using a uniform average to calculate the feedback. So we're doing using a machine learning approach to cluster and organize precipitation data, and then using the least square regression to determine the optimized weights on that. Yeah, I'm not a machine learning expert. This is just an example. Convection clustering of iMerge precip data on the upper right, and on one of the runs with this time was with the ECMWF type closure on the lower side. Another thing we're working on, this goes back to the 2014 GF paper, is we're testing the aerosol impacts on the convection. This is something that finally is moving ahead. It needed a few improvements on what we used to do in the 2014 paper. There's 2 main impacts: the conversion of cloud water to rain. Here we use a Barry conversion. We can also use Karutinov Barry conversion. This is easy to change. And then the precipitation efficiency, that equation there is based on a paper by Zhang and Feingold, where the precipitation efficiency is pretty much proportional to CCN and normalized convective condensate. So what we usually see at the high levels of pollution have the biggest impact on cloud water and ice detrainment in the upper levels, while when the air is very clean, we see a bigger impact on the precipitation efficiency by increasing the precipitation efficiency. Usually the clean air has a bigger impact for us than the dirty air just because of scavenging happening at the same time. That's just one example here of precipitation efficiency. AOD in the upper panels is calculated using just prognostic aerosol emissions to fill water-friendly, ice-friendly aerosols. So there's almost no additional computational cost in this. And then the resulting precipitation efficiencies, the differences actually are below. So it's actually shows that in most areas where it's kind of blue, which is below what we assume was a background AOD value that was used to determine those empirical conversion constants, you see the red color, which is an increase in precipitation efficiency. And then we have downdraft cold pool parameterizations. This comes from Saul of Freitas here. It's a realistic physical process. It also may help another outstanding parameterization problem. Quite often you get convective parameterizations producing precip over mountains, for example, where the forcing is, and then the forcing doesn't move, so the precip from the convective parameterization doesn't move. While in reality, of course, it would move with the flow, at least. So this will actually help that too, and I'll show you an example of that. Now, a parameterization to account for the effects of cold pools. There's a paper by Freitas et al. That describes a very extensive approach where he uses two-dimensional advection, three-dimensional diffusion, source terms, sink terms. So he actually advects the buoyancy excess and then sees where it ends up, and then as a result gets new convection developing like that. I think this might work well on the coarse resolution. So far, it may be very difficult to use that on a higher resolution. We've done the lower part here. This was done by Hannah Barnes about a year ago by just using beta X here, not as the buoyancy excess, but as the downdraft mass flux. And then advecting very simply the downdraft mass flux to also allow the convection to actually move away from just the forcing. And this is the equations from Saul's paper. And what is interesting for us here is what's encircled, the gust front horizontal velocity and the propagation velocity. And these two things we use actually to create additional momentum tendencies. And the gust front we use to actually impact the surface scheme in the MYNN by increasing U star. So there's three ways to implement this: the full implementation as in Freitas et al., or an additional momentum tendency using gust front velocity and propagation speed, which is what we're doing right now at GSL with MPAS-A for HFIP, or adding gust front velocity in surface layer scheme to impact the surface fluxes. And then just one picture here for, this is only a 12-hour run. This is like, this just came out yesterday. We have a 5-day run, but I was not able to get that out in time. What you see without the cold pool, this is a run with GF. The GF scheme actually slowed down the storm a little bit. And then with the simple cold pool in there, so we just add the momentum tendencies, it speeds up again a little bit. And what you see especially also that the wind speeds are stronger, especially in the right front quadrant there, which makes sense because that's the direction of the storm movement in that case. So right here, they're stronger. All right, just one slide on the C3 parameterization. Starting point is the GF scheme, but there's three groups involved: GSL, PSL, CP-TEC. We added updraft vertical velocity from the scalar SAS scheme. And then Lisa Bengtson is one of the main developer leads here too, added the prognostic updraft error fraction computation and a new closure based on updraft velocity. And she's also introducing prognostic updraft velocity calculations. Rain evaporation from the SUS scheme, aerosol indirect effect, I already mentioned that. And the current implementation, as I mentioned, low-level deep shallow routines have been replaced. MPAS driver is as coded by Laura Fowler. We did not change on that because it's a very clean version, except for adding some initializations that are new for the updated GF scheme and are not available in MPAS yet, like stochastic arrays, chem-related arrays. They might be available, but we didn't know what they were called. And so, like I said, it's all very recent work. Second call to GF has been added in that driver for the congestus clouds. Momentum tendencies have been activated. We are running in real time MPAS Dev 2. You can check that on the website. 3 kilometer MPAS Dev 1 without GF. And we will be running for HFIP. All is currently in GSL development branch. I believe we're keeping that up to date with the MPAS master repository. I hope I'm right here. In the future, question is, should this go back into NCAR repository? And also when C3 is ready, should C3 replace GF or be an additional option? My idea is to replace it. And we will have a separate repository for GF and C3, just like for the microphysics scheme. So submodule type approach, but only for the lower level. So like even the GF driver will stay in MPAS. That's it.
Thanks. If you have questions for George, I'm sure you can find him at lunch or the break. So we should move on to our next speaker, which is Wei Li.
I'll be talking about physics interoperability, a small project that we've been doing to connect the M-cubed shared physics that Laura talked about yesterday to the CCPP single count model. So I want to acknowledge all of the contributors who are involved in this small project, mostly from NCAR and NOAA labs, and also, of course, DTC. So in terms of interoperable physics, it is actually a community need because folks need a single and a standardized interface between model physics and all of the host models around the community. So common community physics package, CCPP, that you guys have been hearing a lot about in these 2 days is such kind of a great example in an effort to provide the community such kind of a single and a standardized interface that containing all of the active physics development and also have a excellent connection with different host models. At NCAR, SEMA is currently adopting CCPP for, improving interoperable physics. And as far as I know, CCPP framework is being integrated into SEMA. And meanwhile, many groups across NCAR are converting many NCAR physics like CHEM and M-cube physics into the format or version that CCPP can recognize, which is so-called CCPP compliancy. So yeah, I want to introduce our little project, as I said, to connect this M-cube shared physics to the CCPP single count model. So basically what we do is to make the MPAS mesoscale reference suite functional in CCPP single count model, both technically and scientifically. The purpose is to demonstrate such kind of interoperability of this M-cube shared physics across different host models. What we're talking about different host model is the model beyond the M-cube models involving WRF MPAS and SIM1, but also the models currently uses CCPP framework can also uses M-cube shared physics in this small project effort. And another long-term goal of this project is we want to seek or explore the possibility to see if M-cube models or MPAS SIM1 can also use the physics that are currently, residing in the CCPP physics repository maintained by the DTC. So the diagram below shows some pathways sort of describing what I just said. For example, the red arrow you see indicating other host models that uses CCPP framework. For example, UFS, Navy's Neptune model can call CCPP physics. And since we connect the M-cube shared physics with the CCPP, those model can also, call M-cube shared physics through this pathway. And in the blue arrow, like I just mentioned, we have a hope that to explore the possibility if M-cube model can also call CCPP physics in some way. So this is, sort of an overview of this pilot project. So in this project, we first and foremost, we have to implement the M-cube shared physics in some way that CCPP single call model can recognize. So first step is to treat M-cube shared physics as a submodule. You heard about submodule a lot in previous talks. So basically, M-cube can update their physics on their end, but the CCPP single call model user can call their updated shared physics, at the same time. So this is really nice in terms of code management, also user preference. And another thing that we do in terms of implementation is we want to make sure the physics source code that M-cube developed along with their metadata file meet the CCPP rules and standards. So we have been scrutinizing, take a lot of time doing this to make sure this one works well. And this effort also directly contributed to the physics to be used in SEMA. Because I know Chem team also wants to use some physics from the M-cube group. And another work that we do is to add the glue code or so-called interstitials to connect the M-cube shared physics to the hosts. What we're talking about host is single call model, but also some other host that uses the CCPP framework. So we add those interstitials. And lastly, we have to modify the host side so-called CCPP single call model code to realize such kind of connections. So 3 steps: source code, glue code, and also modify host side code. I did want to mention some features or positives about the CCPP single call model, because in this project, CCPP single call model is such a powerful tool and a robust approach for us to test and implement in a incremental way, and also very nice efficiently. So as we know, the CCPP single call model, unlike some other single call models in the community, is fully compatible with CCPP, which means all of the CCPP physics schemes can be called through this single call model, and which means we have flexible physics choice, and we have some features like subcycling for each physics schemes available in CCPP. So it's really nice. And another thing, like many other single call models, we can decouple the physics from dynamics, which means we can do some hierarchical studies and compare with some real cases. And like I said, real cases are available in single call model, and those are initialized from field campaigns, which provided some reliable benchmark for testing evaluation. The single call model is quick, easy, cost-effective for code implementation, debugging, and process level testing. And lastly, I did want to mention the upcoming single call model release that has some expanded capabilities, including the single call model can be initialized with CCPP enabled 3-dimensional models, just so you can do some replay type of test and evaluation. And also we added more DEFI cases into the single call model. Okay, so another effort that we do in this project is test and evaluation, in addition to implementation, for both technical feasibility and the scientific feasibility. So in terms of technical feasibility, we ran the cases basically using single call model, but we swapped the scheme in CCPP physics repository with the implemented scheme in M-cube shared physics, just to make sure, the implementation is not doing anything crazy. And in terms of scientific feasibility, like I said, we want to evaluate our output against some reliable benchmarks. Those are from field campaigns, observations, and reliable large AD simulations. Okay, so here's an example of how we do this, a sort of testing, evaluation, and implementation, and shows this a suite definition file from CCPP. So here we use the GFS-based REP suite. As you see here, REP basically use the MYN surface layer scheme and MYN PBL scheme, but we replace Not sure if I can use it. Okay, we replaced the surface layer scheme with the M-cube surface layer scheme, and then replaced the MYNN-PBL scheme with the YSU version in M-cube shared physics. So you see for each scheme, they have different components, something pre, and then the source code coming from, WRF and MPAS repository, and then the post interstitials that we added. So I want to explain what is pre and then the source code and post. So basically pre-interstitial help prepare variables passed from host to the M-cube physics. So we prepare variables and then pass to the source code. We didn't touch anything in this source code. And then after this source code, we prepare this post interstitial that can help, with some variables passed back to the host, and also variable used by other parameterizations, after and in between these schemes, and also prepare those tendencies. So these are the work that we do to make this connection happen. Okay, so in terms of testing evaluation, I want to show some examples. Here is a YSU PBL scheme. We compare the version that is previously available in CCPP, which is the old version of YSU, and compare with our implementation M-Cube's version. Red curve shows CCPP version, and green curve shows M-Cube version. And for two cases, the one with cloud and the one barely has cloud, TWPIs and the Wangara day 33. So the major takeaway from this test evaluation is we compared these two versions of YSU and confirmed technically, our implementation works very well in CCPP single call model, but we do see some differences under the condition of being cloudy, but we attribute those differences to different versions of YSU instead of some key differences in the code itself. And this is an example for the MN5 revised surface layer scheme. So what we're trying to compare here is we incrementally add the M-cubes YSU to this M-cubes or MM5 revised surface layer scheme as a combo and compare with the default wrap suite, which has MYN surface and MYN PBL. And compare these two, we find the implementation again works well in CCPP single call model for both temperature and specific humidity biases. And also, the precipitate water. And however, meanwhile, we find actually positively together with the M-cubes YSU, the MM5's revised surface layer scheme actually bring in smaller bias of both temperature, temperature, QV, and the precipitate water. So this is really positive. We're now trying to, compare actually these two because lots of tuning and tweaking are involved in these, different combinations in the physics suite. But what we're trying to show here is it really works well with this implementation. Okay, to summarize, in this pilot project, we connected several physics schemes in the MPAS mesoscale reference suite to the CCPP single call model. And our effort has proved this interoperability of M-cubed shared physics that can be, across different host models beyond the M-cube models, but also those models, uses CCPP framework. And also, we showed the CCPP single call model really is a powerful tool for the community if you want to accelerate implementations of your physics and also do some quality testing evaluation. And we believe this effort, even though it's a small effort, can facilitate some implementation of CCPP in the development of SEMA. And lastly, I want to bring you some future outlook for these projects. So to further enhance interoperability of physics, which is a recommendation from the CCPP visioning workshop last year, we want to allow, if M-cube model can also use physics currently resides containing all of the physics development in CCPP to really, fulfill the purpose of bilateral interoperability. So what we do, what we're trying to do is to explore the possibility to see if M-cube model can call the experimental GFS physics suite. And we targeted two schemes for now, SAS deep and the SAS shallow convection. So this is something in progress and ongoing. So we hope we can, have something positive in future to share with everybody. Okay, I will stop here and happy to take any questions.
Questions? Okay. All right. Well, we'll move along then, and our next speaker is Tracy.
Right. Good morning, or what's left of it. I'll be talking about improving the Earth system models via hierarchical system development. And I just want to point out that this is an effort among a lot of contributors across a number of, you know, places. And so, okay, so first is, what is hierarchical system development, or HSD? So HSD is a concept to provide efficient model development approach spanning simple to complex models with multiple entry points in order to work more easily with the broad Earth system research and modeling community. So on the on the right is the schematic of HSD testing of model components. So on the top is the physics process simulator, single column models, so these more simplified models, and the bottom going towards these complex, fully coupled models. And so you can do process level assessments along all of these entry points or levels of HSD testing for the model components. And as you use these simpler models, you know, your understanding of the processes is greater, but as you get to these fully complex models, your understanding of those processes is lower, but you have a better understanding of the full systems. And so HSD, as I said, provides simpler versions of a more complex system, so it's easier to work with and understand. It provides a testing pathway for updating new innovations from, say, the research community via like your R2O or your research to operations testing pathway. And it's a more efficient use of compute resources. So why do we need hierarchical system development? So there's numerous Earth system processes to model from, you know, the local on the left, say land atmosphere interactions. There's numerous ones to the regional and global interactions. And so to understand model biases, we often need to start by simplifying the Earth system model down to a few key processes and interactions to make sure that we're getting the right answer for the right reason. And as I said, it's an efficient use of compute resources, and we need these simpler models to really identify and fix bugs early on in the testing process before we move on to making those longer model runs. So hierarchical system development has been talked about for quite a while. Back in 2016, there was a WCRP climate workshop. The climate community uses hierarchical approach to understand model components and behavior. They had another one back in 2022. Also, numerous collaborators have written papers or documented things, such as Tim Palmer, said hierarchical thinking should be second nature for all weather and climate scientists. Julia Slingo from the UK Met Office said that we need to increase focus on process level understanding in making model improvements and connect the weather and climate research and modeling. Kirsten Jakob in a BAMS article said our community needs to improve diagnosis of processes contributing to model errors. We need more model developers and not just model users. Christian also had this a schematic for the HSD R2O cycle for helping to improve, you know, model errors from the research community to the developers. So you're starting with your Earth system model, looking at one of the Earth system model components, you do a model assessment, find processes and phenomena of relevance, select suitable process studies, that you can perform detailed studies using your HSD tools at various entry points, and they include multiple configurations. And then those findings are passed on to the development team that can design system improvements and assess impacts across applications. And that's really an iterative process here until everyone is happy and satisfied to integrate it into the Earth system model. And so you can read more about that in Christian's article. There are a number of tools out there or software to support HSD. The first one that's been talked about already is the Common Community Physics Package. It is a library of physical parameters, which can be grouped as physics suites, and a framework or infrastructure that connects those physics to the host model. It's designed to really lower the bar for community involvement in physics testing and development through increased interoperability, improved documentation, and continuous support for developers and users. And the CCPP and its companion single column model enables users to more efficiently connect the HSD steps. As has been said, I think already, CCP has already been integrated into the NOAA Unified Forecast System, UFS, for both global and regional NWP applications, and it's currently being integrated into NCAR and NRL models, and leverages the NOAA NCAR MOA on sharing model infrastructure. And you can read more about it at the link there. Another tool that supports the HSD approach that is used widely is the MET Plus, or the Model Evaluation Tools Diagnostic and Verification Software Package. So the MET Plus verification software is for NWP and other Earth system components and models for various HSD steps, and it includes metrics, including at the process level specifically. So you can look at errors and tendencies within your columns or soundings or profiles compared to observations pretty easily, looking at S2S diagnostics such as planetary waves, multivariate relationships, aggregating a number of cases to look at model systematic biases, and so on. There's just a slew of things that you can look at. So they're just some high-level examples of tools that are used for HSD. The Developmental Testbed Center has done a lot of physics testing and evaluation using the single column model specifically. The first in the list here is the MAGIC from the MAGIC campaign, the Marine Arm GPCI investigation of clouds, looking at the transition of stratocumulus to cumulus transition off the west coast of California. And that was run looking at the single column model. One of the findings was that the physics failed to capture the shallow cumulus transition in a C to C transition regime. And so that can be looked at further using the single column model to see, test different physics parameterizations and see what's going on there. The CCPP physics suites was evaluated across scales for a hurricane case, looking at 3-kilometer convection allowing models, 13-kilometer global medium range, and the 25 subseasonal to seasonal resolution, as well as the single column model. The finding with those was that the physics suites did not produce scale invariant results for forecasts of temperature, cloud cover, precipitation, or TC track. And then the last example of looking at this in a hierarchical way was looking at the ARM Southern Great Plains site, looking at PBL surface layer and cloud processes over land. So this was looking at single column model runs compared with LASSO LES runs. And the finding here was that the single column model produces weaker radiation inversions with stronger entrainment and capping inversions, yielding excessive clouds. And so, yeah, there's a lot of work being done looking at these various cases and even other cases that also are included in the single column model repository as well, to do this physics testing and evaluation. So another thing that was done was looking at establishing community requirements for HSD. And so this was something that I was leading, and this was specifically for the Unified Forecast System, but it is applicable to all models and Earth system models. So we were creating a white paper to define the current state, the future needs, and the recommendations for HSD for the UFS. It was a collaborative effort between the DTC, the Earth Prediction Innovation Center, EPIC, and the community. And this was done by a broadly distributed survey to gather insights and feedback from the community as a whole to help shape the future of HSD. We had a number of responses from the survey, over half were research scientists and postdocs, but we also had professors, faculty, software engineers, managers, and other people participate. One of the questions in there was trying to prioritize HSD tools, so ranking them from 1 to 5, 5 being the highest community priority. And everything was pretty highly ranked. But one of the things that the community was really interested in was having case studies that they can use to test among these different HSD entry levels. A nested domain, this is, again, this was geared to the UFS, but it can be applicable to other models as well. The community wants to be able to do cloud resolving, so those lower resolutions. Idealized simulations, so having that capability of, say, a one-stop shop to do idealized simulations. The next one was mechanism interaction denial. So being able to use these various tools to, say, for example, the single column model, which denies your dynamics feedbacks, or say an aquaplanet, which denies that land mechanism, and so on. And then the variable resolution and the lowest ranking was the large eddy simulation. And from all of this survey, as well as, open-ended questions, we were able to put together recommendations for the UFS forecast system for this HSD development. So this is just the challenges and opportunities for HSD. So Earth system models for weather and climate are becoming increasingly complex with many processes and interactions, and we need to really get the right answers for the right reasons. HSD is a systems engineering approach that tests these small elements. So your smaller, your simpler models, for example, your schemes of a Earth system model first in isolation, and then progressively connect those elements with increased coupling between your ESM components. So HSD can help improve understanding of spatial and temporal dependencies in model physics. So we want to see consistent solutions between models and applications at different resolutions. And, right now we don't necessarily see that. And also the HSD process is concurrent and iterative. So, the more complex HSD steps can provide information to be used at simpler HSD steps and vice versa. And then the CCPP and its companion SCM provides an efficient infrastructure and set of physics that connect HSD steps, where CCPP is under active development by the DTC and the community, with new parameterizations and framework capabilities being added continuously. And then MET Plus software provides verification and diagnostics that includes process level metrics, also under active development by the DTC and the community. And as I had mentioned, it's a wide collaborative effort among Earth system research and modeling community on the use of HSD for a more effective model improvement process. For example, our collaboration effort for UFS for that HSD white paper. All right, thanks.
Questions? Okay, I guess everybody's interested in lunch, and I'm sure we can all talk offline. Thanks to all the speakers. Thanks for good timing, and we'll see you after lunch.
I think it's on, right? Test, test. Yeah. All right, I guess we might as well get started. Is the speaker here? All right, this is like a two-part presentation, I suppose. First part on evaluation of regional to local predictions using surface and satellite data. I hope I don't mess up your name, Yi-Yu Yang.
Yes. Thank you. Good afternoon, everyone. My name is Yi Yang. I'm a second-year PhD student at Northeastern University, and I'd like to highly appreciate the organizer committee for offering such great opportunity for me to share my research on multi-scale modeling of air quality and greenhouse gases over Greater Boston. Let me start with some brief introduction for the background. My work is part of the project Super Impact Engine sponsored by Northeastern University. Currently, cities and towns have been making air pollution control policies based on the regional average from sparse networks stations. And in our project, we aim at identifying hyperlocal hotspots by combining densely installed low-cost sensors and the novel air quality models to support more sensible policymaking. As we all know, the ground level ozone and particulate matter are two components of the criteria air pollutants, which can adversely impact human health, especially the children and the elderly. And carbon dioxide is a major component of greenhouse gases. Over the past 1 to 2 centuries, carbon dioxide has caused the global warming effect, and such effect is tend to continue in the future. The greenhouse gases can alter the local meteorology and thus indirectly impact the formation and transport of air pollutants. And in this work, I'm using the model WRF-Chem GG to simulate both air pollutants and greenhouse gases with a single set of simulations. And here are the 3 tips of my observations. First, I will assess the model capability of reducing air quality related variables and their sensitivity to grid resolutions. Based on that, I will identify the underlying reasons for model biases in typical summer and winter months to inform potential areas of prediction improvements. Finally, my model results will be passed to offer the background conditions for hyperlocal strict scale modeling MYNN-EDMF, which will be covered by my colleague Ying Wang in part 2. And in this slide, I'm showing the model setup information for my simulation. And we designed a triple nested domain over Greater Boston at grid spacing of 12 kilometer, 3 kilometer, and 1 kilometer. In this table, I summarize the chemical inputs and part of the chemical options for my model configuration. And in addition to the baseline simulation, I also carry out 2 sensitivity simulations to test the model response to changes of chemical inputs. And here, I also use a series of observational data from both surface network and satellite to do the model evaluation. And here I include the data source for different variables. The performance for air pollutants and carbon dioxide is my focus, and the analysis of other variables would help me to comprehensively analyze the underlying reason for model biases. Further, to quantificationally judge the model performance, I also adopt a series of model evaluation protocols recommended by the previous work or established in our group to judge the model performance for some key meteorological variables, ozone, PM2.5, and carbon dioxide. Then let's take a look at the model performance. Here on the left, I use a Taylor diagram to summarize the model performance for all the meteorological variables I've evaluated. The Taylor diagram can summarize the model performance in terms of both standard deviation and correlation coefficient. The pink dot on the x-axis represents the observational dot, and the radial curve represents the standard normalized standard deviation, which carries the information of relative amplitude of variation. And the outside arc represents the correlation coefficients. Generally, the closer to the observational dot, the better the model performance is. And on the right, I use a soccer plot to summarize the model performance for temperature, wind speed, and wind direction. Here, the values are normalized by the absolute value of the benchmark, so all the metrics will become dimensionless. And as the plot shows, the wind speed shows the strongest sensitivity to fine grid resolutions. And for temperature and wind direction, they display different patterns in different seasons. For wind direction, for the temperature, there are larger cold biases in January, while it falls within the benchmark in July. As for wind direction, it falls within the benchmark in January, but a larger growth arrow is shown in July. And here, I'm also displaying the temporal trend of several key meteorological variables at the Logan International Airport site in both months. As we can see, for temperature, relatively humidity, and wind speed, WRF-Chem GHG generally well reproduces the temporal trend, and with better reproduction at finer grid resolutions, especially for temperature and relatively humidity in July and wind speed in both months. For the precipitation, there's low observations in January, which is best reproduced by the 1 kilometer grid resolution. And in July, there are some heavy precipitation events which are best reproduced by the 3 kilometer resolution. Following the results for meteorology, I'm also displaying the performance statistics for many chemical species. And in this plot, I'm displaying the evaluation metrics for in the results at 1 kilometer resolution. The gray dashed rectangle represents the recommended benchmark for ozone, and the brown dashed rectangle represents the recommended benchmark for total PM 2.5 and carbon dioxide. As the plot shows, the performance for ozone and carbon dioxide are both good, since the biases are within the benchmarks for both months. And for PM 2.5, in July, it is moderately underpredicted, but the bias and errors are still within the benchmark. In January, PM 2.5 is overpredicted, and such overprediction is attributed to the overprediction for almost all PM 2.5 components, including elemental carbon, organic carbon, ammonia, nitrate, sulfate, and unspeciated PM 2.5. For the cloud variables, AOD, CCN, and CF, they are all underpredicted in both months, with larger biases in July. And I'm also displaying the model performance for ozone and PM 2.5 in terms of the overlaid spatial distribution. As the ozone maps show, the WRF-Chem GHG can well reproduce the magnitude of its mixing ratio. But due to the fact that the ozone network station is sparsely distributed in my domain, we can hardly tell whether the model is able to capture the spatial pattern for ozone. And for PM 2.5, luckily, we have more observational data from both the AQS surface network and the purple air sensor data. The PM 2.5 in January is overpredicted, mainly due to the high localized emission in urban center. In addition, at the finer grid resolutions, the dispersion of PM 2.5 can be inadequate, and such limitation can further lead to the accumulation of local PM 2.5. And following that, I'm also displaying the the spatial distribution for ozone and PM2.5 in July. For ozone, WRF-Chem GHG slightly underpredicts its mixing ratio, but the normalized mean bias are still within the 15% benchmark. And for PM2.5, WRF-Chem GHG slightly underpredicts its concentration, mainly due to the failure in reproducing the long-range transport from the Great Canadian Wildfire happened last year. And in addition, looking at the zoom-in plot, we may notice that there could be one more sensors collocated on one single grid, but they record different magnitude of PM2.5 concentrations. And this indicates that even the 1 kilometer is not fine enough to capture such subgrid variability. So even more hyperlocal model is in demand to reproduce such variance. And I'm also displaying the temporal trend for ozone and PM2.5 in 3 representative cities in Greater Boston: Roxbury, Chelsea, and Brookline. For ozone at Roxbury, both the temporal trend and the magnitude are well reproduced by WRF-Chem GHG. And for PM2.5 in January, generally the temporal trend are well captured by WRF-Chem GHG, indicated by a high correlation coefficient. As for July, both the temporal trend and magnitude are well captured, except for the Canadian wildfire days. And the large underprediction on Canadian wildfire days lead to the total poor correlation coefficient. If not considering these Canadian wildfire days, the correlation coefficient for PM2.5 in July could reach around 0.7. In addition to the baseline simulation, I also carry out 2 sensitivity simulations to test the model response to changes in chemical inputs. For the first sensitivity simulation, it is designed for January by reducing the primary PM2.5 emission. And as the results show, the overprediction for EC, OC, sulfate, and the unspeciated PM2.5 are reduced. And as EC and unspeciated PM2.5 are treated as only primary in WRF-Chem GHG, and in winter months, the secondary organic organic carbon reaction is not active. So the OC is also almost linear primary in January. So the response of EC, OC, and unspeciated PM2.5 is almost linear in January. Another sensitivity simulation aims at using a different database for the chemical boundary condition. In my simulation, the chemical boundary condition comes from the global model vacuum. And in the baseline simulation, I'm using the vacuum with fin as the wildfire emission. And in the sensitivity test, I'm testing using vacuum with QFAD as the wildfire emission. And in July 2023, QFAD will estimate higher wildfire emission than fin dataset. And as the figures show, as the statistics show, with the use of vacuum QFAD as the boundary condition, the underprediction of ozone and PM2.5 is slightly reduced, but the response is trivial. And such trivial response may further indicate some limitations in the long-range transport of air pollutants. Yeah, let me sum up my today's talk. Generally, for most meteorological variables, the WRF-Chem GHG can well reproduce them in both months. For ozone and carbon dioxide, WRF-Chem GHG performs well as their normalized mean bias and normalized mean error all fall within the benchmark. For PM2.5, it is overpredicted in January due to the high local emissions, and it is underpredicted on Canadian wildfire days in July. For most meteorological variables and ozone, WRF-Chem GHG performs better at finer grid resolutions. As for my future work, I will further improve the model performance by addressing uncertainties in meteorological and chemical inputs, as well as the model treatments. And here are my acknowledgements. I will stop here and I'm happy to take any questions. Thank you for your listening.
We got time for one quick question. Okay, and we'll go to the next talk.
Thank you.
Thank you. Part two from Wang.
Good afternoon, everyone, and thank you for giving me this opportunity to share my work. And next, I will focus on the second part of the multi-scale air quality modeling work with a focus at the street level. The accurate predictions of hyperlocal air quality is essential for us to understand the urban air quality distributions and the human exposures. Here, I make a diagram showing the major processes could affect the street-level air quality affected by traffic emissions. We can see much complex interactions between the local meteorology, the roof-level chemical concentrations, reactions, and human patterns. Unfortunately, regional air quality models have limited skills on such hyperlocal scales. So people developed the urban air quality models at the reach high resolution and with a focus on the dispersion and transport of air pollutants. Among them, the newly developed street network model called MYNN-EDMF can couple with the SSH aerosol model, making it has the ability to simulate the gas phase chemistry, aerosol chemistry, and dynamics at a hyperlocal scale. As part of the iSuper project focusing on the over Greater Boston, the first objective of my work is to intercompare the performance of such hyperlocal air quality model MYNN-EDMF with the regional model WRF-Chem over Greater Boston. And as the traffic emissions are the major source at Street Canyon, so we would like to assess the impact of traffic activity data on the on-road emissions and street-level air quality. We hope this product could help identify the hyperlocal pollution hotspots and distribution to improve the local air quality regulation. I think most of you may be not familiar with this model, so let me briefly introduce the MYNN-EDMF. It's a newly developed street network model. It represents a street network into two components. The concentrations are calculated in the Street Canyon, assuming they are distributed unified. The vertical transport are calculated with the background concentrations above the roof level. As for the horizontal transfer, they are calculated at the street intersections. Here I have a flowchart to show the data flow in the model. It needs information on the weather conditions and roof level chemical concentrations, street level traffic emissions, geometries. Then the model can simulate the street level pollutant concentrations affected by emissions, transport, chemistry, aerosol thermodynamics, dynamics, and deposition. Talking about my test bed, here I choose the Greater Boston. If you have ever been to Boston, you will know how busy the traffic is. And based on the NEI 2020, the traffic emissions contribute to 20% of PM 2.5 emissions and 5% of greenhouse gases emissions. Here we test the performance in January and July last year. As mentioned earlier, the background concentration and meteorological predictions are simulated at 1 kilometer from WRF-Chem GEG from my college. And in this work, we use a model called WIN to simulate the street level emissions. And the different with the WRF-Chem GEG. Here in the street network model, we use sectional bins to represent the aerosol size distribution, which is considered to be more accurate. Talking about the vehicle emission estimation, here we use the bottom-up approach to simulate the hourly emissions at the street level from exhaust and non-exhaust sources. In this method, the accuracy of the emissions are highly affected by the traffic activities, including mainly the traffic flow, the type, and fleet composition. However, such information are not always available. So here we developed two cases to represent the traffic activities and see how they impact the traffic emissions estimation and corresponding air quality modeling. In the first case, we use the annual average daily traffic from the Massachusetts Department of Transportation to represent the flows, and the hour diurnal profile of vehicles mile traveled to distribute it into the hourly profile. The speed are estimated from the speed limit. In this case, the emissions are highly affected by the road type. In the second case, we collect the traffic flows and speed from the simulation from the transportation planning model called Transcade. It simulates the traffic activities based on social economic data and some capacity at each street. Let's see the street level emissions on the weekday in July. Here we can see that the ADT case, the emission hotspots are mainly located along the principal streets like interstates and principal arterials because of their higher traffic volumes, while the Transcade case gives higher estimates in most cases. With that emission, we simulate the street-level air quality using this Munich SSH model and compare it with the WRF-Chem GHG. Here are some snapshots of the results in the January. Compare the spatial distribution, we can observe much stronger spatial variations and more hotspots along the street in the Munich SSH model, which cannot be reviewed by the original WRF-Chem GHG. In January, we evaluate the performance with the AQS data and the purple air neural data. And unfortunately, we can observe a much higher overprediction in PM 2.5, since it's January and there are light generation from secondary organic aerosol. So this overprediction is mainly attributed by the meteorological conditions and the emissions. From the morning of cutoff length, the atmosphere in January is quite stable, and the wind speed, temperature, friction velocity, and PBL height are all underestimated. This leads to the accumulation of air pollutants at the street level. And by diagnostic evaluation, we found that the primary PM 2.5 are overpredicted. Therefore, we conduct emission adjustments sensitivity test and to reduce part of the primary PM 2.5 emissions, and we found this could effectively reduce the overprediction, and the both models respond linearly to this emission adjustment. And after the adjustment, and the WRF-Chem GHG has the lowest bias, and compared with the two observational data, we can see a higher bias in the low-cost purple air because of the uncertainties in the measurement and the location. In general, with higher PM 2.5 observations, the performance are much better, and the difference between the two models are smaller. Like in January, the difference between the street level and model and WRF-Chem GHG can be as high as over 1 microgram per cubic meter. In July, it's less than 0.5. This is due to the well reproduction of the meteorological conditions that contribute to the dissipation of pollutants. But still, we see the underpredictions and poor correlations. Therefore, we look into performance at each site on out days and see that the underpredictions are mainly happened on the 1st of July and middle of July, affected by the Canadian wildfire event. This indicates some limitations in the wildfire emissions and the long-range transport of the wildfire. But on the other days, the performance are pretty satisfactory on different types of streets. Here I plot the results on local streets and the principal arterials. I can see that with the higher traffic volume, the difference between the two emission scenarios are also higher. This aligns with the emission distribution. Here we compare the PM 2.5 simulations from the two emission cases in July and January. in the two traffic activity data can lead to as high as 8 microgram per cubic meter in difference in PM 2.5, but generally the average difference is 6%. And then in the Munich with the Transcade case give estimates higher PM 2.5, especially on the except on the heavy traffic streets. To give a summary here, we simulate the 3-level hyperlocal PM 2.5 using the WRF-Chem GG and Munich SSH models. We found that the traffic activity data can significantly impact on-road emissions estimation, especially on the heavy streets. And the PM 2.5 predictions are better by the Transcade case. And compared with the WRF-Chem GG, Munich SSH could effectively identify the hyperlocal pollution hotspots. The results are satisfactory in July, and in January, the overprediction is due to some limitations in the meteorological prediction and emissions. Given this, since some of the results are preliminary, and I'm still working on to refine this work. So I will first improve the on-road emission inventory to improve the fleet composition using some neighborhood-specific data from the automatic traffic recording. Also, I will work with my colleague on improving the background conditions from WRF-Chem GG, especially in January. Thanks for your listening.
Thank you also for making up so much time. We have time for questions.
We have an online question. Did you test different gas phase chemistry mechanisms such as CB6, which can be considered as an improved version of CB05?
Oh, okay. Thank you for the question. That's pretty good. And here the reason we choose CB05 is to make it consistent in the WRF-Chem GG and the Munich SSH. I believe CB05 is available, mainly used in the SMAP, but here in our WRF-Chem work, we focus on the CB05, but later that's a very good direction. Thank you for pointing it out.
I also had a question related to how you handle the vehicle fleet effects. I was curious if you take into account the ambient weather conditions, which will have an impact on the level of emissions for a particular vehicle class, in addition to things like age and the other factors that you referenced.
Okay, thank you. Thank you for the question. And actually, the estimate of emissions is more complicated than what I have shown here. The emissions are affected not only by the traffic activities, but also the meteorological condition like the temperature, the humidity. And even if we have very similar traffic data in January and July, the meteorological difference results in the total difference in the emissions.
Yeah, that was essentially my question. So
yeah,
you answered that.
I hope I answered your question.
Yes, you did. Thank you very much.
Thank you for your question. Thank you for all of your attention.
Yeah. Seemed like the biggest difference between your just forefront and your one that used Munich was that in some of the major streets, the concentrations were much higher in the Munich run.
Yes.
Is that right? And but you really had no way to evaluate that, right? Did you have any monitors on those streets?
That's a pretty good question. And actually, our iSuper project also working on to install some low-cost sensor data along the major streets that will help the evaluation of this work, because mostly like the AQS sites of the low-cost sensors they are not directly on the streets or close the streets. So what we could do first, when evaluation with the purple air, we choose the near road sites, which is less than 50 meters along the roads. We hope this could better represent the concentration in Straight Canyon. Meanwhile, our project is working on to install some sensor data sponsored by our university. And now they are in the stage of calibration and the evaluation. And when that's ready, we will use that data to evaluate our street-level air quality predictions.
So you will get some monitors in the major streets in the street canyons?
Yes.
Yeah, that's very important.
Thank you.
I just follow up on John's question because that was kind of my question, representativeness, right? Because the AQS is not designed, right, to measure in these urban street canyons. But I was just curious, your experience with Purple Air, how many of those were getting kind of closer to those like urban street canyon environments?
Okay, and think first, I will say also most AQS streets are not long, but EPA developed some near road streets, and fortunately, there's one near road street over Greater Boston, and we can use that to evaluate the NOx and PM 2.5. And for the Purple Air, although there are lots of sensors, but they are low cost, so there are larger biases. First, we use, okay, I will make it quick. First, we did some data cleaning to using the two channels from the purple air to reduce the bias. Then, which based on their distance to the main street, we choose part of close to streets to try to make it more accurately represent the street level concentrations.
We'll have to move on.
Thank you.
Okay, thanks again for the timely talk. And next speaker is Shima Shams. We're switching continents, I believe.
Hi, everyone. My name is Shima Shams. I'm a project scientist here at NSF NCAR. Today, I'm going to talk about a project that is very close to my heart and is focusing on enhancing air quality decision-making activity in Eastern and Southern Africa. I would like to acknowledge all of my collaborators and colleagues involved in this work. So detrimental effects of air quality is well known to all of us, but I have a few examples here to show the critical importance of studying this matter in Africa. More than 23,000 premature deaths is tied to air quality in Eastern and Southern Africa. In Kenya, only about 20 million of population are dealing with respiratory diseases. And here I borrowed a figure from Institute of Health metric that shows that in Rwanda, both in 2009 and still in 2019, that is the last estimate that they had, air quality is the second most important factor which is the driver of death and disability. And when we talk about air quality issues in Africa, there are quite differences from what we deal in North America and Europe. And everything that I mentioned is just talking about the current condition. There is an expected explosive growth in population of these regions, which would be tied to growth in anthropogenic emissions on top of large seasonal biomass burning activities, the dust storms. It's just showing how important and urgent it is to better understand and provide insight and monitoring, and hopefully moving toward evidence-based decision-making in these regions. The other side of motivation of our work, which has chemical data assimilation, is that in these regions, it's been shown that because of limitation in our emission inventories, as well as meteorological and boundary condition limitation, as well as some still limitation that we have in chemical schemes, such as organic secondary aerosols and nitrate. If we just have WRF-Chem runs, there would be large biases compared to observation. So to this end, to work on such project, we got funded through NASA Surveyor to work on a project which utilized chemical data assimilation to co-design and co-develop a regional air quality forecast for Eastern and Southern Africa, together with their local scientists, to provide near real-time air quality forecasts up to 2 days and be able to provide information to create awareness for public and decision-making. Aside from that, we also will create tools for them to look at atlas of past 2 decades and the trends of air quality in the region. So I created the schematic diagram to help to better understand this multifaceted project. We have very strong stakeholder engagement in this work because we wanted to understand the needs, priority, and challenges of stakeholder agencies in each country. And based on those, we're designing the system. We have a very strong data collection, data processing, air quality control for observation. The key observation that we are using, database that we're using in terms of air quality and atmospheric composition is WRF-AOD, TRPOMI-CO, and for the Atlas of Air Quality, we are using global reanalysis of CAMs and surface observation for validation. So the core part is doing the chemical assimilation, incorporating WRF-AOD and TRPOMI-CO into retrievals of WRF-Chem to design these, to have these air quality forecasts, and then having the evaluation system, source attribution, and dissemination platform. At the end, you see a capacity building and transition of new capabilities, but this is not going to happen at the end. At each stage of project, we are closely working with our stakeholder, which you see their logo at the bottom part of the slide. So the initial stakeholder engagement is besides the trips that we had and in-person talk that we had with a couple of agencies, we designed a survey that had different components from having their to better understand their organization background, what the stakeholders they have, how agencies in each country collaborate with each other, and what mandates they have, what they need to provide to each other, and what are the air quality capacity challenges that they are facing in each, and had a component on education and training. The survey was distributed to top-level air quality related agencies in countries, and we were asking for senior staff to help us with their knowledge of these questions. We had 14 responses from these institutions from 5 countries of Rwanda, Kenya, Ethiopia, Malawi, and Uganda. And they represented different agencies from National Weather and Meteorological Services, academic institution, and space agencies. I'm sharing one of the results with showing that more than 78% of participants mentioned that they do not provide air quality forecasts to the public, although it is part of their mandate. We don't have time to go over all of the survey results, but I felt like this part about the education and outreach has a good synergy with this work, which is showing that all our participants recognize the benefit of training workshop for WRF and at all levels, from beginner, intermediate to advanced. And then in addition to that, we had a section and they all mentioned that they would benefit from science communication training so they can better translate the meaning of air quality data and be able to communicate that to different stakeholders and target audience, including the decision makers. This is the WRF-Chem data assimilation system design. So we work with WRF-Chem and WRF-DA for these data assimilations. Main key parameter of focus are ozone, PM2.5, PM10, and all related species such as NO2. The grid is spacing 15 kilometers. The forecast is going to be up to 2 days. I mentioned that WRF-AOD and TRPOMI-CO will be incorporated in this work as we want them to be able to go beyond the lifetime of MODIS and be able to use this framework. The anthropogenic emission, we are using CAM's annual data set. And for fire emission, we're using FIN version 2.5. And for people who don't know about it, it already includes the active fire from MODIS and WIRS, biogenic emissions from MYNN, and gas phase chemistry Mozart, Aerosol processes GoCard, and meteorological data from GFS, boundary condition vacuum. And we are developing the main system on derecho HPC here, but we are also working with Metro Rwanda to have everything installed on their system. In addition, we are also working on another installation on AWS so we can distribute it and all of our stakeholders be able to use the system. We are still working on that system design, so I didn't have exact results of this project, but a similar work that we have done in on India, and we expect to get similar results and possibly and hopefully even more improvement is because this work over Delhi was only incorporating MODIS AOD, and in the upcoming work we are working with VIIRS AOD and TRPOMI-CO. But overall, to understand these plots, basically the black line is showing the observation of different sorts from satellite, in situ and ground observation. Red is WRF-Chem, just a background run, and then the assimilation is blue. And in all cases, you can see how it gets closer to the observation. For the system attribution, we have done a similar work, but this wasn't through assimilation, just a WRF-Chem base run. And just to help us to better understand where are the sources of each, and similar methodology using the tracer of CO and black carbon would help us to provide some information on details of that. On the capacity building, one of the key part that came out of the survey was to provide some easy to use software for their staff scientists to be able to look at trends and create maps. So we developed some Jupyter notebook, looking at CAMS data set, be able to create some trend analysis as well as seasonal maps, or be able also to change the duration and period based on their interest. And the code is available through GitHub. We are working on the installation of HPC through Metro Rwanda, and also upcoming workshop would be at the end of the stage of project to go over different steps of run. And for dissemination system, our team through both ACOM and RAL has extensive expertise in creating usable, simple, user-friendly dashboards for air quality data dissemination. We will utilize these capabilities to share our results. With that, I'd be happy to have questions.
Very interesting work. I'm always glad to see WRF-Chem being used effectively in third world countries too. Any questions? We have time.
It's very nice to see this ambitious and important project. I was curious if you're doing any validation or simulation of weather observations, and in particular, if you're leveraging TOMO.
TOMO, I'm not really familiar with that weather.
That's the Trans-African Hydrometeorological Observatory. It's been run by TU Delft for many years. In your 15-kilometer domain, there might be a few thousand stations.
That's a great point. So far, we've been mostly in touch to, especially with Finland and Canopy, that they are also installing some new sensors for air quality measures. But in the past work, we always used ground-based observation, as you see in this work, for the GFS validation to know the impact of meteorology and also know the accuracy of them. But I'd be happy to be in touch. Yeah,
offline I can provide you the connection.
Thanks for mentioning it.
Thank you.
Any online question? Oh, okay. Well, thanks again. The name. All right. That would be Ajay. Right. Ajay, talking about vertical transport and wet scavenging of aerosols.
Hello, good afternoon, everyone. I'm Ajay. I'm a postdoc accommodation under NSF NCAR. So today I will be showing some of my preliminary results on vertical transport and wet scavenging of aerosols in WRF-Chem simulations for deep convection during the Seekers field campaign. So first of all, I would like to thank my supervisor, Mary Beth, and all other co-authors who have constant helped me throughout my study. So we all know that aerosols play a key role in the keeping the radiation balance and also in the cloud formation. So one of the major process that really determine the lifetime of aerosols in the atmosphere is aerosol scavenging, and it also decides the extent of their downstream impacts. So during these convective activities, what happens to the aerosols that get lofted up into the upper troposphere? So from the boundary layer, they get transported up and they enter the cloud, and some activate or merge with the cloud droplets. And the updraft in the cloud loft these aerosols upwards, whereas some of these aerosols get rained out. And whereas the rest of the aerosols exit at the top of the storm. So the scavenging, which is generally we can call it as removal. So scavenging efficiency is the term that decides what fraction of aerosols that enter the base of the cloud do not make it to the top. So one of the major questions that the scientific fraternity is working on is what is the scavenging efficiency of the inorganic and organic aerosols such as sulfate, nitrates, ammonium, organic carbon, etc., and different types of convection. We all know that the aerosols like sulfate show high hygroscopicity, whereas the others like organic carbon, which shows low hygroscopicity. So what is the scavenging efficiency of these aerosols? So to understand this, there has been several field campaigns like DC3 and Seekers happened over the last many years. So Seekers is one of the campaign which happened during the August and September 2013 over the Southeast US, where they measured the convective storms over Mississippi and also over Gulf of Mexico and South Texas. And here we can also see the convection sampled in the southern US and the magenta circles. And earlier studies have really studied on the scavenging efficiency of trace gases. For example, I have mentioned those papers too in here. So the main objective of my study is that how well does the cloud scale and regional scale WRF-Chem really represent this convective transport and also the scavenging of aerosols in different types of convection. So here is an illustration of the model grid points representing the clouds. So for that, we are concentrating more on the September 2nd Seekers storm over Mississippi, where the DC-8 aircraft have penetrated into the prefrontal convection near Jackson, in Mississippi. And they have measured one air mass storm and also one multi-cell storm. So we have configured the WRF-Chem simulations to represent these storms as part of the Seeker analysis studies. So we have performed the regional scale simulations with the parameterized convection at a resolution of 12 kilometer, and these provide a boundary conditions for the cloud scale WRF-Chem. And these cloud scale WRF-Chems are performed at a resolution of 1.3 kilometers, and the domains are shown in the figure. And we are also representing the aerosols using the mosaic Forbin aerosol scheme. So first of all, it is very necessary to see how does the WRF-Chem really represent the convective storms when in comparison to the NEXRAD observations. So here is an animation which shows the NEXRAD observed radar reflected in the left and the WRF-Chem simulated convective storms, small convective storms in the right. And here we can see that irrespective of the difference in time and location of the convective storms, the WRF-Chem reasonably represents the convective storms which were intercepted by the DC-8 aircraft, and the observed and model cloud reflective magnitudes are also similar. So to look into more into the radar reflectivity, we drew like the CFAT diagrams, which like shows us the height versus the height. Sorry, the vertical reflectivity. And here we have compared it for two rainfall category, light to moderate in the upper panel, and we are also showing the heavy rainfall category in the down panel. And here we can see that even though there is some difference in the convective storms from 8 to 10 kilometers in the heavy rainfall category and all, in general, WRF-Chem really captures the vertical structure of the atmosphere, permitting a comparison between the model and observations. So then let's look into the clear error profiles, which were made between the 16 and 22nd hour UTC, just to look into how comparing the model simulated chemistry with observations. So the blue lines are the WRF-Chem and the black dots are the DC8 observations. And we can see that for some of the species like SO2, the model really underestimates, whereas the WRF-Chem has, in generally, it has some good agreement with the observed vertical profiles when you look at the aerosols. So now I would like to, as I already mentioned, there was one air mass storm and another multi-cell storm were measured by the DC8 aircraft. So I would like to show an example how we interpret the results from the WRF-Chem. So in the left, you can see the NEXTRAT maximum reflectivity at 1810 UTC, where you can see the air mass storm. And into the right, it is the WRF-Chem simulated convective storm at 1810. And we can also see the convective, the reflectivity, the vertical profile of the reflectivity, which shows that the storm height went up to 8 kilometers, which was well represented in comparison to the observations. So the simulated cloud core was chosen to represent the DC8 aircraft intercepted cloud core. So next, I would like to show an example of the aerosols. So what I'm showing in the left-hand panel is the sulfate in the units of microgram per meter cube. It is a summation of the first three bins. That means PM 2.5 sulfate portion, which comes under the PM 2.5. And into the right-hand side, it is the difference between no scavenging and a with scavenging simulation, the difference between that, which really shows that, sorry, a really good amount of aerosols would be scavenged when you compare these simulations. So using these, comparing the radar, the simulated radar reflectivity, and also the cloud ice water content, and also the positive vertical velocities, we selected few grid cells at the 8 kilometer simulated cloud core to represent the convective outflow region, which were intercepted by the DC8 observations. I will also like to add that the shown example was just for sulfate. We did for other aerosols species too. And now we would like to jump into the multi-cell storm, where in the left, again, it shows the NEXTRAT observed reflectivity, and into the right-hand side, we can see that there is a delay in the convective storm. We can see the convective storm, the multi-cell convective storm in the WRF-Chem simulations at 8 an hour. But again, it very well represents the observations, and it also shows that the cloud core, it went up to like 8 kilometer vertically. So then we would like to determine the scavenging efficiency from these results. So we performed like two simulations, one with wet scavenging and another without wet scavenging. So, and the equation for wet scavenging is as shown here. And the left table shows that the result for the air mass storm, where the DC8, for example, for sulfate, the DC8 measured the scavenging efficiency at 88%, whereas for the WRF-Chem it was between 50 to 60%. And whereas for less hygroscopic species like organic aerosols, for the DC8 measurements were up to like 66%, whereas the WRF-Chem again was in 40 to 50%. And also similar results were also seen in the multi-cell storms. So I would like to these are some preliminary results. So these WRF-Chem cloud-scale simulations satisfactorily represent these small convective storms, and the clear air profile has some good agreement with the observed vertical profiles. And these cloud scale simulations generally represent the convective transport well. And also the next steps, what we would like to do is to compare these cloud scale and regional scale simulations, like again with the observations and more extensive analysis of aerosol scavenging. That means we have to look into more storms, and also to understand process like nucleation scavenging and impaction scavenging, their influence on the scavenging of aerosols in WRF-Chem. Thank you.
Again, we have a lot of time for additional questions. Looks like we have an online question.
They want to know if dry scavenging is included as an updraft lifting the aerosols.
Yes, yeah, because this is mosaic aerosol scheme that we are using to represent the aerosols. So yeah, but we are mostly concentrating on the wet scavenging. So we have done simulations, one with and without wet scavenging. So the difference should be because we would like to continue quantify only the difference due to wet scavenging. Yeah.
In the previous slide, it seemed like the WRF-Chem was consistently underestimating the scattering, scavenging efficiency relative to the DC8.
Yeah.
And I'm just wondering, is it possible to update those?
Because this is just, as I earlier said, this is just one case that we have studied into. So the ultimate goal is really to look into to make modifications to these models, like because there are a lot of assumptions which goes into the models regarding the scavenging efficiency, which really determine the lifetime of aerosols. But just with studying one storm, it's really tough to make a modification.
Are there more field campaigns, DC8 type or DC?
Yes, there are most we are further looking into. There is a September 18 convective storm over Gulf of Mexico. It's a CCAR observed camp, and also there are like 5-6 other storms studies made from DC8. Yeah.
The wet scavenging here, is this from the large scale, so from the microphysics scheme?
Yes, but when we are looking into the cloud scale, so it's like convective permitting. Yeah. So
Okay.
now we are looking, the current sort simulations are only from the convective permitting simulations. So we are also looking into the regional scale simulations and later compare those with the.
Right, but on the cloud scale, it's not inside the microphysics routine, right? It's the wet scavenging that is done inside the chemistry driver.
Yes.
Yeah.
Yes.
Okay.
That's true.
Any other question? No? Okay, then we'll hand it over to.
Thank you. Thank you.
How to improve dust simulations.
So yeah, good afternoon, everyone. I'd like to begin thanking my co-authors, Pedro Jimenez, Rajesh Kumar, and Senlin He. And this material is really mostly Pedro's that he led. I'm just presenting it on his behalf. But as we know, dust is an abundant atmospheric aerosol that affects both direct and indirect aerosol effects. And dust emissions are very sensitive to both soil moisture and wind speed. And because as you increase soil moisture, you increase the cohesive forces between the soil particles. And that can lead to dust storms and things like that. So our objective in this project that was funded by NASA is to increase our really core fundamental understanding of how soil moisture modulates and affects the Earth's radiative balance through modulations of the dust emissions. And so a couple of the specific questions that we wanted to look at are, what is the impact of soil moisture modulations in the dust radiative perturbation? Won't be talking about that today. That's a future paper coming out later this year, hopefully. And then what is the added value of assimilating SMAP, the NASA's soil moisture active passive satellite soil moisture retrievals for dust simulations? And that's what this talk will be looking at. So we've taken a couple of different approaches. One was looking at 8 case studies of dust storm events. And so that's work that I led, and that paper was published in January of this year in Atmospheric Environment. And then second, which is more the subject of this particular talk, we're extending the analysis beyond case studies. We're doing year-long simulations in order to provide a more statistically robust characterization of the impacts of soil moisture on dust emissions. This paper, Pedro's leading it. It's submitted to Monthly Weather Review. And I'll just add that in the lower, cool. So in the lower right corner here, this just shows the SMAP retrievals for ascending and descending paths on one particular day, regridded to the 9-kilometer CONUS domain that we're using for our studies here. So our experimental setup for this talk, so we use two different dust emission schemes, the GoCart and GoCart AFWA. And then, so we use those just without modifying the soil moisture. So that would be over here. And then in this panel, we add in the direct insertion of the SMAP soil moisture. So we won't be talking here about the positive and negative anomalies in the soil moisture. We're just doing this, basically this experiment B here. We also have an experiment where we took out all the dust emissions entirely. That's in the paper, but not in this talk due to space constraints. We also, and for reasons that I'll explain, for the GoCart AFWA experiments, we also played with reducing the dust emissions pretty substantially, all the way down to 5% of what the default is in the AFWA scheme. So we used WRF-Chem version 4.2.1, a 9-kilometer grid over CONUS. Our initial and boundary conditions come from the MERA-2. We used the GoCart aerosol model. And we also connected the GoCart aerosols to the Thompson-Eidhammer aerosol-aware microphysics in order to account for aerosol indirect effects and scavenging. As I mentioned before, we use the GoCart and GoCart AFWA dust emission models. I'll just draw your attention over here to the right. So this shows basically how sensitive the two dust emission schemes are to soil moisture. And so the GoCart scheme is here in the dashed gray. And because the moisture correction just hovers right around 1, no matter what you do to the soil moisture, it's really not going to have any impact in the GoCart scheme. But in the AFWA scheme, it becomes very sensitive, or at least a lot more sensitive than GoCart is, to soil moisture. And so that's why we're interested in looking at AFWA as well. And so we have direct insertion of the SMAP soil moisture retrievals every 12 hours. So we do WRF-Chem experiments both with and without soil moisture from SMAP. Like I mentioned, we do with the AFWA dust emission scheme, doing bulk reductions of domain-wide reductions of the emissions. And we started our simulations on the 1st of January 2015 and run through the end of March 2016. We throw away the first 3 months for spin up. And so we have a 12-month or year-long evaluation period, basically coinciding with the start of when SMAP became operational. So diving into some results. So basically, how does WRF do with soil moisture representation, and how does SMAP do? So over this 1 year case, so on the right, we have just the GoCart. So this does not have any SMAP corrections. This is just the model doing what the model's doing. And then on the left, we have what SMAP had in comparison to in situ observations from USCRN. And we see really over the Western US that the GoCart model or WRF-Chem is really too wet over the Western US, and that's where most of the dust producing regions are. By comparison, SMAP has much smaller biases. So SMAP has errors and problems in other parts of the US, but in the dust producing regions, which we care about in this talk, SMAP is a lot more accurate than the WRF model. So we know that we can by inserting SMAP into WRF, we should get more accurate soil moisture, and hopefully that'll help us with dust. So we can calculate skill scores in order to really compare which experiment is better than the other. I'll just point out that this on this map over here, the yellow, orange, and red regions, this shows where in WRF the dust erodibility is greater than 0. Basically, you can't have dust emissions anywhere where the erodibility is 0. So the dust emissions really are confined to specific regions, especially in the southwestern US. And so at these USCRN sites, so this is again looking at soil moisture, we see really across the dust producing region, we see that when we add in or when we insert SMAP into WRF-Chem, we see improvements for the most part in the soil moisture representation. So we're at least improving that aspect of the model. But so in theory, that should be, that's a good thing to do, even if it causes other issues downstream. So looking at how does this impact the aerosol optical depth? So we compare it against Aeronet stations on the left, and then MODIS Terra retrievals on the right, again over this 1-year period. And so we see that there's against Aeronet, there's not much bias when we just do the go-kart SMAP. But then when we switch to the AFWA scheme, the AFWA dust emission scheme, now we're seeing very large positive biases in aerosol optical depth in the Southwest. And we see that both in Aeronet and in MODIS Terra. And so this is indicating to us that the AFWA dust emission scheme is putting out just too much dust. And so that was part of the motivation, along with also my case studies paper, which I mentioned earlier. This was part of our thinking for, well, AFWA is just emitting way too much dust. And so in order to get it down closer to what the regular go-kart scheme is doing, we decided to do some, give it a trim down to 50%, 25, 10%, and even down to 5% of what the default is. And once we found that once you get down to about 25% of the AFWA emissions, maybe 10%, so somewhere in here, then you get rid of, for the most part, this positive bias in AOD in the Southwest. And it doesn't really do a whole lot of damage to the rest of the country, but we're really trying to improve what are the actual dust emissions in the Southwest. And so going down to 25% really does seem to help. And so doing another skill score comparison here. So I color coded the numbers. So where you see the blue, say in this top left panel, this means that the 50% emissions experiment is better than the 100% emissions experiment. So where blue is shown 50% is better, where red is shown 100% is better. And so really, again, we're focusing the action on the Southwest. So we see big reductions or big improvements going down to 50%. Even more improvements going down to 25% of emissions. But then once we go down to 10%, we don't see a whole lot of extra improvement. And then by 5%, there's really no difference, 5% versus 10% emissions. So that's part of where we're recommending probably stopping at 25% to get it to about the right amount of emissions. So then if we restrict this to basically just the regions where erodibility is greater than 0. We see that we're, again, the skill score showing that the go-kart AFWA with SMAP insertions is better than just go-kart AFWA. We see that once we reduce the emissions, that then we can see more of the benefits of inserting SMAP soil moisture into WRF-Chem. And so we see more of these improvements at 25% emissions, but at 10% emissions, we don't see a whole lot of improvement. And we even see some damaging and degradation of the AOD around West Texas and Southern New Mexico area. So more reason to stop at 25%. So looking at kind of a histogram, so what this chart is showing is comparing MODIS Terra AOD 550 retrievals, again, just in regions where the WRF dust erodibility is greater than 0. The black bars indicate the 25% emission reduction, and the hatched bars down to 10% emission reduction. And again, it's showing bins for the skill score. So what we see is that for the 25% emissions scenario, this distribution is positively tilted, showing that we see more improvements than we see degradations. Whereas for the 10%, it's very much a symmetric distribution. This is again arguing for why going down to 10% emission, 10% emissions is probably a bit too far and unnecessary. So in conclusion, we found that inserting SMAP soil moisture retrievals into WRF-Chem produces around 20 to 40% improvements in soil moisture in the Southwest, where most of the dust is produced. It harms the soil moisture in other parts of the country, however, so it's not a universal solution. So it's more complicated. Dust emissions we also found appear to be, I would say, grossly overestimated in the Go-Kart AFWA dust emission scheme, particularly in the Colorado River Delta region. And a reduction in the emissions down to about 25% is needed in order to have a similar dust loading as we have in the standard go-kart emission scheme. After reducing the AFWA dust emissions down to 25% of their default value, then we see a small added value in imposing the SMAP retrievals. And we believe that if we're able to better inspect the realism of other aerosol species, including the accuracy of the retrievals themselves, reducing the bulk amount of dust that's emitted, and also revisiting the definition of the source regions in the model, that may contribute to improving further the value of the retrievals. I'll just add that in from the case studies work that I did, I found that basically this high dust emission region in the Southwest was just churning out unrealistic dust storms every day in the model, at least the days that I looked at. And also there was another a derecho event. So those of you here in Colorado may remember December 15th, 2021. There's a derecho that moved from Colorado up to Wisconsin. It shut down I-70 due to high, just basically zero visibility from dust storms. But there's zero erodibility in WRF there, so it can't emit the dust. And so WRF can't get that right, or WRF-Chem can't get that right. And so we really do need to take another look at the erodibility data set in WRF-Chem, possibly have it time varying as well to account for extended flash droughts and things like that. So if you have questions, I can answer some of them, but also encourage you to email Pedro Jimenez. Thank you.
Time for questions. Probably you, yeah.
So you kind of got to my question at the end there, is that I've always found that erode data set that comes with WRF to be more useful for like global scale dust, like Saharan dust transport, versus especially in the Southwest US, it's kind of taking too large of an average because it's really highly erodible dry lake beds that are a huge source, and then broad areas that really aren't. And so I've always had to modify that heavily to get WRF to do something nice, because like you said, it just kind of broadens out those dry lake beds. And so you end up with these large areas of diffuse dust versus actual realistic plumes coming from the actual erodible areas.
Yeah, excuse me. And that's, we didn't look into actually modifying the erodibility field or data set itself. But I think that's a really important thing to do. And we've found also that, for instance, Great Sand Dunes National Park here in Colorado, no erodibility. But we can see from satellites that it's often producing a dust plume. So yeah, we need to have modifications to that.
I'm Sandra LeGrand. Nice to meet you. Thank you for your work. So a couple of things with the experimental design. There was a change in the deposition scheme for WRF-Chem dust that corrected things basically falling out of the atmosphere too quickly. So your 25% reduction is probably a reflection of that correction, and that's not changing the empirical tuning constants that were designed for before that correction was changed. So it's about the right scale that I would expect to see. Okay. The other thing is the deserts in this part of the world are very green. And AFWA does not include, at least the default that's in WRF-Chem does not have a drag partition component to it or something that accounts for the wind shear stress due to plants at the surface. It's just a very crude 1987 greenness plot that just masks out perennial vegetated areas. So that's also another kind of motivating factor why you're getting too much dust if you're using the default scheme. We do have a correction for that. We were actually planning on pushing that to the MPAS go-kart when it eventually comes around, but we do have the code available on a GitHub site with a GMD publication if you're interested in using that. And then the last thing I'll touch on with the with that study, and it's kind of like universally acknowledged that the dust emission, the source region or the EROD file in that is not representative in this part of the world. It's meant to find mega lakes like what you would find in a Holocene type of things in the Sahara and stuff like that. And you're right, the erodible sources there are much smaller. We do have a new dust emission scheme adaptation for that accounts for the geomorphic composition of fluvial and aeolian deposition dust sources. Again, also planned for release through MPAS. But if somebody would like to work with that, it also does work with WRF-Chem. And please contact me if you're interested in learning more or want to use that. I'd be happy to share.
Great. Thank you for sharing all those additional model improvements. So I'm glad we're on similar tracks, showing similar things, and glad to hear that that'll be in MPAS soon.
Let's take out the dust source region and let the soil moisture and a more representative vegetation map do its thing. Probably see more realistic spatial distributions of dust emissions part of the world.
Great. Yeah, that's a great idea. Thank you.
All right. Well, thank you. And we have one more speaker. Follow myself.
Hello, I'm here. A very good afternoon, everyone.
Prakash Yadav.
Yeah. Good afternoon, everyone. My name is Praful Yadav. I'm working in Indian Institute of Tropical Meteorology. And I'm going to present today the evaluation of advanced air quality forecasting and decision support system for effective pollution management in Delhi. I would like to acknowledge my supervisor, Dr. Sachin, Dr. Rajesh, Dr. Gaurav, Dr. Chinmay, and Dr. Rajmal. To start with, as we know, Delhi is one of the most polluted and populated city in India. So for the control the pollution in Delhi, the government of India has started National Clean Air Program in 2017, under which they have told us to build the air quality early warning system to for the precautionary measurement for the Delhi residents of India. And then this program has started in 2018, and then additionally in 2021 the DSS, decision support system, has been came into the picture for for the policymakers of Delhi to take the precautionary measures and to implement the graded response action plan for pollution management. So this is the workflow of air quality early warning system and decision support system that we run in IITM. We are running WRF-Chem version 3.9.1. We are taking the initial condition from the IITM GFS, and this IITM GFS is running in the with a GFS model, and some changes has been done according to the regional initial condition. And then we are using the chemical inputs of anthropogenic emissions, chemical boundary conditions from the vacuum, anthropogenic emissions from EDGAR. The EDGAR emissions has been regraded with the system of air quality forecasting from SUFFER project, and for 400-meter resolution. The air quality early warning system is running for 400-meter resolution, and we have upscaled the 400-meter resolution from Delhi to northern part of India, and we are running for 10 days of forecast for northern part of India, and then 3 days of forecast for Delhi with a 400-meter resolution. This we are taking into consideration the fire emissions from the fire climatology that we have built, and the fire inventory from the NCAR. And we are taking the input from active fire from MODIS and VRS data. Then we are applying the chemical data assimilation 3D VAR with the GSI and simulating the model, simulating the observation and chemical chemistry for next 10 days of forecast. And apart from this, we have built the DSS, decision support system, which runs with 400-meter resolution, which runs with the 10-kilometer resolution. We have included 400 tracers for 5 days forecast. And these tracers are basically for source apportionment and for study the emission reduction scenarios. We are giving the source apportionment measurement measure for PM 2.5 to Delhi government, and also we are including the emission reduction scenarios for public. Then this forecast has been post-processed and then goes to the web dissemination. This web dissemination goes to the public, and then this IMD, Indian Meteorological Department, prepares the bulletin based on the forecast. There is a government body, CAQM, Commission for Air Quality Management, has been established in 2018 and under the government of India. And they have implemented the action plan, which are says like GRAP 1, GRAP 2, and GRAP 3. These are the graded response action plans, which has as GRAP 1 and GRAP 2 more on the side of precautionary measurement, like they shut down the use of coal and diesel vehicles. And then GRAP 3 and GRAP 4 are mostly shutting down some industrial areas based on the diesel and petroleum. Yeah, the air quality early warning system, it was has been designed for Delhi, not only for Delhi. We have implemented for Pune, Mumbai, Ahmedabad, Kolkata, Bangalore, Hyderabad, and Jaipur also for 2 kilometer other city. So the WRF-Chem setup we are using is we have parameterizing the cloud microphysics with WRF single movement 6 class scheme, shortwave radiation rapid radiative transfer model for GCMS, and then surface layer air Monin Aboko scheme, land per surface scheme, unified NOVA land surface model, then MYNN 2.5 boundary layer scheme, cumulus physics scheme for 10 kilometer domain. We are using Grail-Freitas ensemble scheme, and then gas phase chemistry was using Mozart, and aerosol phases chemistry as a go-kart. So the domain one covers the total Indian region of 10 kilometer, and then we have domain 2, which covers the central the Delhi and surrounding regions of Delhi, includes Haryana and some part of Punjab, and then domain 3 basically focused on Delhi region. So the some silent feature of the Indian air quality forecasting system is that it is 400-meter operational air quality prediction system that was developed to predict the extreme air pollution events like Diwali, like dust storm events, and the biomass burning period. This is we are using real-time observation of air quality over the region. We are using the fire count AOD assimilation from the MODIS. Right now we are in the stage of implementing the VRS assimilation, and then this air quality forecast is available for 400 meters for next 3 days for Delhi region. And we have around 40 stations which are from the Central Pollution Control Board, which covers total Delhi, Delhi and surrounding districts like Haryana. And this is the box whisker plot. I just wanted to mention we have evaluated the system for 5 years because it's running for 5 years, and the box whisker plot tells the evaluation of forecasted PM 2.5 concentration at 400-meter horizontal resolution over Delhi from October to January, because this is the period where Delhi air quality is in the peak period, which is the Delhi air quality goes beyond PM 2.5 concentration about 200 microgram per meter cube. Just wanted to tell that recent database from the World Health Organization and tell that only the Delhi has contributed mean annual PM 2.5 concentration of about 120 microgram per meter cube, which is the huge number. and living in Delhi is very difficult right now, and there are no precautionary measures. It's just that we can build the decision support system, and we can give the forecast, and we can implement some strategies based on the graded response action plan. So then we have evaluated the medium range air quality forecast. This is the air quality forecast. We have taken one case for the of 2022, where we were able to capture the peak pollution event during the Diwali event. Diwali is the event. Diwali is the festival where the people burn the lots of firecrackers. And during that time, we have a winter period also. There are also western disturbances. So the peak pollution episode has to be there. So we are evaluating the forecast for 10 days. So our medium range air quality forecast, 10 days forecast for this Diwali occasion has predicted well in advance for the event occurred on 25th of October. Then the overall performance of statistic for mean PM 2.5 for 3-day forecast period has been evaluated. This PM 2.5 forecast for 3 days has been evaluated for total 5 years. The performance says that the index of agreement is very close. It's very good in the case of first day and second day forecast, and we have moderate performance in the case of third day forecast, as the forecast performance deteriorate and the because we are using 3D VAR and due to uncertainties in the model. Then we have calculated the forecast skill score for various air quality index categories for 3-day forecast period. The air quality index category are based on the PM 2.5 range, very unhealthy category where the AQI, air quality index, is more than 200. Then very unhealthy category where the air quality index is greater than 30, critical where the air quality index is greater than 401. So we have seen that the accuracy of the air quality forecast for 3 days for the first day is 90%, where the probability detection is very high, where the success ratio is also high. The performance diagram depicts the same. The second depicts for the first day of the forecast. Then second day of the forecast has a good accuracy in case of unhealthy and very unhealthy category. But in case of third day forecast and critical category, we have moderate performance. So then we have evaluated our air quality early warning forecasting system with the other model, which are giving the similar forecast for of different agencies, like ECMWF is giving CAMS, GUS FP NASA, GUS ML, NCEP, NCMRWF, which is another institution of India for medium range weather forecasting, and the SILM, which are running in the Indian Meteorological Department. We have compared the results, and we have found that when predicting the unhealthy category, where the air quality index is greater than 200, the probability of detection is around 95 to 97% for in case of air quality early warning system. And then the second is like CAMS, where the probability of detection and success ratio is very low, but yeah, they at least predict the air quality forecast for the 3 day for advanced 3 day, and there is like moderate performance while predicting the air quality index and critical category. Then we have extended the multi-model approach and evaluated the performance index based on the different institution giving air quality forecast, and we found that the air quality early warning system having like a very good skill. And second number is GUS-ML, NASA GUS-ML, and then SILM as acceptable, where the NCMRWF has acceptable and poor, where the CAMS and NCEP is having a very poor performance. Yeah. And then we have the results from the DSS. DSS is basically decision support system, where we have included 400 tracers based on the emissions which are there from different sectors of Delhi, like transportation, brick lanes, etc., and the emissions from other districts surrounding Delhi, and the emissions from biomass burning period. So the grab stages has been like incorporated during 2022 and 23 period and 23 and 24 period, we have found that implementation of restriction in stage 2 result in AQI reducing the air quality index by 5 unit, and where the stage 3 on top of the stage 2 result in reduction of AQI by 10 to 15 units, where the stage 4 of GRAP results in reducing AQI in city by high as 60 unit, which is the large reduction. Then to summarize, this study provides the overview of air quality early warning system and decision forecast system, which highlights the main findings of DSS that assisted the policymakers in making the science-based decision for management of air quality in the city of Delhi, and the system performance has improved over the years. Then the high value of index agreement and low minimal like mean fractional bias indicates the exemplary performance, classifying both the first day and second day PM2.5 forecast, which is kind of excellent compared with the other models. And the overall statistical analysis underscores the commendable performance in the very unhealthy AQI category, while the critical category exhibits a moderate skill level. The total AQWS and DSS showcase the commendable performance over the years, with enhancement attributed to improve the data assimilation and emission inventories. Thank you.
We have time for a quick question. One online question.
What are the model details of the 400-meter model? What is the runtime of a 3-day prediction?
Like from the analysis, the model details are this only. We are using the same physics suits, and yeah, we are using the Edgar STAP emission inventory. Merged and integrated with the system for air quality forecasting and research emission inventory, which has been developed by Ministry of Earth Science only. And then we are using the gas phase chemistry as Mozart and aerosol phase chemistry as Go-Kart, and we are also implementing the chemical data assimilation from AOD and surface data assimilation for 400 from 400 CPCB sites, Central Pollution Control Board sites.
Okay, thank you. And I guess we're going to have a little discussion session now on chemistry. And I think I'm going to go here so I can take some notes. See what's coming up. So what's on my mind, and some of the GSL folks, probably NCAR folks too, as the first question is, what are we going to do with WRF-Chem in the future? Now, about 10 years ago, I think this came up, maybe not quite 10 years. This came up the first time we were going to shut down WRF-Chem because there was no funding. Well, there's still no funding. Development is still happening, but we really now think about it's time to at least stop the development. And because we're all going to shift more and more towards MPAS. At GSL and NCAR, we certainly are. Now, we know there is a lot of people out in the world, third world countries especially, that are using WRF-Chem. We still get requests for tutorials. Last time we helped out was in Peru a couple of years ago, which was actually great, gave us a chance to see Machu Picchu. But these things are major efforts. If there's new development work, running the regression tests and trying to get that into the community version is a pretty difficult task. So at this point, we tend to say, we don't want to do any more of this regression testing. We would help somebody maybe if he wants to get something into the community version still, but it'll be, we don't like to, let's say. There'll still be some support from us if there's questions. The forum will still keep on going if people are using the forum. There's quite a few people who are trying to use the WRF forum, the WRF-Chem forum too. And tutorials is also very difficult. It usually takes a long time to set up anything on other computer systems. So that we could also really, since we don't have any funding for this, only support in absolute minimal sense if organizing institutions already make sure everything is running on their computer systems. Anybody has any comments on this? Or $1 million to support WRF-Chem?
Well, it seems like the obvious question is, when is something like MPAS-Chem going to be available with what fraction of capabilities of WRF-Chem?
Yeah, that's a very good question. And again, WRF-Chem is still there. It's not going to go away, right? I mean, people will be using it. There's no question. That's a good question, though. When is MPAS-Chem available? Now, MPAS in general, there's already two different options there, right? There's MPAS-CMAC. And well, Mary, you go ahead. Go ahead.
Well, that's a good point, right? So yesterday we heard about MPAS with CMAC and that it will be released later this year. John can speak more to that than I can. I spoke yesterday about our beginning nascent efforts of moving towards MPAS with chemistry. Hopefully there's some go-kart capability end of this year, but who knows, right? And who knows if it's even ready for support, right? That's a different question. If you remember my last line about MPAS with chemistry, resources are very limited. And so we're not promising anything, and we're trying to work with partners to make things move along. It was an echo of yesterday afternoon's conversation where we're finding the solution of going to work with partners as a way to advance our modeling tools.
Yeah, and we're certainly happy at GSL and CSL to help with that too. Hopefully we can collaborate closer in the future to make sure things don't drift apart too much too quickly. But it is a serious question, you know, when will we be able to come up with something there? I mean, not everybody likes to run CMAC if it has, what, 200 some prognostic variables. But you have a lot of choices too with respect to chemistry, right? But it's probably, there's only one of them probably available in MPAS, right?
Right now, we can do CB6 or we can do Crackham. Crackham 2, Crackham 3. The Crackham's even bigger. It is big, it is slow. And I forget what Jeff was telling me about how long it takes to run. Like if we're gonna, you know, when we run relatively coarse mesh, it's quite reasonable. We can run it for years, like when we do 120 kilometers, but that's, you know, that's not really what we want. We set up a domain lately that goes 60 and then 12 over the continental US and then 4 over California. And he's estimating, we've run it in MPAS. We haven't run the MPAS CMAC of that mesh yet, but he's estimating that's going to be like 1/4 real time. So it'll take like 4 days to run a day. That's not all that practical, but you know, you can do things, obviously. It'd probably be good to get some faster chemistry or something. Yeah.
Sandra.
I can really appreciate the amount of effort that's gone into the continued support and also future development on shoestring budgets, especially because of all the nuances that go into this. We're kind of at a state where We're still tinkering with WRF-Chem because it's comfortable, we love it, and it's easier to develop concepts. But because of the like well-known comment that this is fully community mode anymore, and without like a dedicated agency looking to support her for future effort, it makes it very, very difficult to get dedicated funding for something that isn't necessarily the best viable tech transfer pathway. While at the same time, the MPAS version, we don't have a clear definitive timeline on that. So same thing, I can't easily go to somebody and say, please give me $5 million to share with partners, because I can't guarantee at the end of that cycle that there is a guaranteed tech transfer. So I think right now it's just kind of, it's difficult to figure out how to play in this space to help be good stewards of this collective community because of the uncertainty on timelines. But we love the products though. So it's like we want to help, but I'm not sure how to best do that quite yet.
Yeah, I think, I mean, for somebody who's working like for the dust parameterization, that's probably the easiest way to still help. Because, for example, for MPAS, for the regional version, we need dust in there. We need dust, we need fires, just for, because we need to come up with something that has the same capabilities as her or Rufus operationally.
Right. So currently our way ahead forward with that is to almost treat it like it's a land surface model, so we can at least get the IO parts right and just put a tracer on it. But like the final stage is, how do you connect that back into the atmospheric part? You know, obviously we can't do it, but we can still make forward progress on it. It's just we're trying to skirt the line of how to do this in limbo before the sunset ends, and you know, you have to go and do your demonstrations and capability. But yeah, I think there's definitely a desire to help develop it and keep it moving forward for atmospheric chemistry, at least from our perspective, from a numerical weather prediction forecasting support.
Yeah, if you're looking at other viewpoints with respect to MPAS and how fast something is going to be available, right? I mean, we could go ahead and just throw something from WRF-Chem into MPAS. It's a quick and dirty solution. But then again, we'll end up with even more different versions, which we don't really want to do. What we would like to do from a NOAA point of view, so to GSL and CSL, is see whether we can't get MICM and Musica stuff going fairly quickly, like next week. Well, you've got some resources.
I think there have been definitely discussions going on, numerous discussions with NOAA, with other partners, to see what's the most feasible way to get us to a stable functional system that we can start opening up for community developments. We are just not yet there to say any specific timelines or anything, because we still also need to look into resources. But I think a main criteria is that we understand the need that people need to know where to focus their developments, knowing that specifically WRF-Chem is going away. And so one of our main objectives is have a first stable version that people can use already for first research, but it also allows co-development from the community. But we want to do it in a really strategic, much more organized approach than we have maybe done with WRF-Chem. We don't want to have millions of options that some work with some other feature and some don't. We want to have it really following much more modern software engineering and software design. So that's kind of one of the objectives. That's why just the design phase takes also a while.
Yeah, I guess NOAA we have what we call UFS CAT-CAM. It sounds like a parallel development, but hopefully we'll be able to use MICM at least, which is part of Musica too. So that would kind of make this combined again and require a closer collaboration also with the NCAR folks. Anybody else wants to speak for a different country, different developers? Go ahead, Uli.
Hey, good to be here. My question or thoughts are maybe not directly on the modeling system themselves, but rather on the, like came up on here on a few lectures ago on the availability of input data, particular data for land surface, like the aerot. And then I've also been thinking about with these rapid refresh updates capabilities. From my point of view, for instance, we are basically limited by which satellite data we can acquire from NOAA. So we could have a develop our system into a rapid refresh lookalike for regions where we have access to the current RAP satellite data, which are updated every hour, but that's not global. So how would we go about getting the satellite data?
Well, you still should have the capability to have those data. Actually, in a higher resolution, the Rufus will probably cover that same area, RFS, except on 3 kilometer resolution. And of course, you can also always get the GFS, right? But if you're not using WRF-Chem, you're just using RAP.
Well, we are using WRF-Chem, so things we want to test out is the new data simulation capabilities to using surface chemistry or in combination with other types of assimilation. But as for the satellite data, if we are, well, I'm personally interested in South America and Brazil region. So to set up a rapidly updated forecasting system for that area. But we don't have the know-how to process the satellite data so they would fit into either WRF-DA or most likely JEDI.
So you need something that will work with that sort of automatically.
Idiot's Guide to. I realize this is not a trivial task. I just want to emphasize that.
Yeah, and like I said, we don't have funding.
I'm very, very well aware of my absolute lack of know-how in this region.
Yeah, I mean, I don't know how long you're going to be here. You're going to leave over the weekend again, or because our freightas from Brazil is coming to visit here next week, and be a good place to talk to him about this too. But, all right. I think I need to. Way is looking at me like you better stop soon. Okay, online comments.
There are 2 comments and then a question. One comment is maybe we can move to MPAS-Chem, but we can continue making improvements to WRF-Chem and at the same time use that to update MPAS-Chem. The next comment is it's certainly a heavier lift to run MPAS-CMAC than it is to run WRF-Chem. And then the question is, what are some difficulties when moving WRF code to MPAS other than the large amount of code?
Was the difficulties in what? In
moving WRF code to MPAS other than the large amount of code. I guess this is specific to WRF-Chem.
Right. That's doesn't matter. Anything from WRF, whether it's chemistry or whatsoever, it's very easy to move that into MPAS. But we don't want that confusing complexity in a model anymore. That's what we hope will MICM and Musica give us, a much cleaner way of doing things. But moving code from WRF-Chem, I mean, I'm getting pretty old. I could move any chemistry within 2 weeks into MPAS-Chem.
If I may just also bring up a perspective here. You're right. I mean, you could make a very quick and dirty solution. Whoever asked a question, you could be very quick and dirty. Just hitchhike, take the WRF-Chem code, stuck it into MPAS-A, and beautifully you have maybe something that's running. But first of all, it would be a system that you can no longer maintain. It's going to be messy, and it's just not that you can get any structure in it. We are also, you have to keep in mind that WRF and WRF-Chem have been developed over decades, right? So software engineering, software design, all of that has very much evolved in time, and the codes don't meet modern software engineering standards anymore. So this is an opportunity for us actually to develop now a system that really is up to date, state of the art, and that we can easily maintain and extend in the future. And and that's why design is really important in that phase. And maybe just one other point also to make is there is a lot of processes in WRF-Chem that haven't been fully updated, like MAGAN biogenic emissions. It's not updated to the latest MAGAN version. So you would also have to spend quite a bit of time on WRF-Chem to update some of the key processes to the latest standard. So by developing MPAS-A with chemistry, we actually have the opportunity to really bring in the latest state-of-the-art processes and also follow modern software engineering.
What was that first comment again? Seems like I should have responded there too.
I think you kind of have. I
Okay,
think both
good.
of you kind of touched on that. It was about moving MPAS-Chem to WRF-Chem.
Oh, okay. All right. Okay, well then, before Wei gets too mad, I think I'll better quick. I mean, we can continue a little bit talking about this. Okay.
So I have a question that maybe it's my lack of knowledge that it happened before, but is there going to be or ever was a community workshop to show that how much impact different communities from different countries would be impacted if we stop continuing the support of WRF-Chem? And similar to what NASA usually does with the amount of damage that this would creating a funding support, if you have any comments on it.
Well, those are good ideas too. I mean, I know there's a lot of groups that WMO has already told me, what, you're not going to support WRF-Chem anymore? But again, you got to find funding if you really want to continue, at least on a supporting level, maybe not developing so much, except bug fixes or whatsoever. Yeah, but yeah, there's at this point, there's no plans for that. Ranjit Soki, and he's busy with air quality in Africa too. And there's other folks that are really hard hit, they say, by no more support for WRF-Chem. So that's why we're saying, well, we're going to keep minimal support at least.
I just have a little update on what it takes to run MPAS-CMAC. If you use like a 60 around the world and 12 over the CONUS, takes about a week to run a month.
To run what?
It takes about a week of computer time to run a simulation of a month.
1 month, 1 week, 1 month, so 1 to 4.
Yeah. That's 500 cores. That's a lot of cores. And he points out, I was communicating with Jeff. He points out that if you do a regional MPAS-CMAC, it's equivalent to a WRF-CMAC.
All right. Okay, well, I think, sorry. I'll let Wei take over. Thank you. And if there's more concerns, questions, talk to me, send me email, or we can talk more about it tomorrow. I mean, like Sandra said, I was in management. I get back into this stuff now. Some of us really love WRF-Chem, so.
Thanks, George. Let's switch gear a little bit here. Before you head out for the coffee break, let's give the poster presenters a chance to introduce themselves. So there are a number of them submitted one slide poster presentation. So we're just going to have you line up here, maybe. So it's just one slide per person, and goes by the poster number. So first, yeah, Robert, okay. Yes, okay, thank you.
Thank you.
Rob Gillum, US EPA, and my poster is on an evaluation tool that we use at the EPA for both air quality and meteorology. My poster is kind of focused on the meteorology component of that. And just real quick, the process flow diagram that I have here, just to illustrate or kind of give you an idea what it does. It takes, a model, WRF MPAS, observation data set, fuses them together, puts the data in a database, and then there's a number of ways you can pull those data out and do model evaluation. So please stop by and learn a little bit more about AMET.
Poster number 2.
Hello, everyone. My name is Daniel Shu. I work at Northeastern University, and I have the chance to present. This is part of results from a project. It was a very short term project. So the general goal was to apply the ChemX model. ChemX is the comprehensive air quality model, and together with WRF. So we want to apply this model in Southeast Asia. So it's kind of the Middle East region. And we want to evaluate the model, and we want to check all the bias that we can fix, try to fix this, get good results. And after, the end goal is to apply this model to do some source apportment, study some ways to improve the air quality, some strategies to reducing emissions, and some kind of process analysis. Okay, so in this project, we have the chance to play with these models. So this first figure is the diagram of the modeling system. So we put this together. We don't have a lot of modeling results for this region, so it's kind of new. So we are using the WRF model to drive the ChemX model. So in that way, we can give the best possible meteorological inputs for the model. We also are using emissions from EDGAR, so it's a very coarse resolution. So we also did this from scratch. And the next important emissions are the natural emissions. For example, oceanic emissions, we need to do some work on this. And some very important emission for the region is the dust emissions. So we are using a wind blow dust scheme that is integrated, not integrated, but is part of the ChemX system. So this is very sensitive to wind speed. So there's another, so it's double the importance of word results. And of course, we have inputs from ozone column and boundary conditions and initial conditions from global transport models. And everything goes to the ChemX model, and we do some, and we can analyze these results. So the very first step for us was to set up a few simulations. So we have something like a few winter cases, or a few summer cases. This first table is a comparison of the baseline. So we start with some configuration and the final configuration. So with this final configuration, we have different options of physics, and we also have inclusion of data simulation, and it improved a lot the model results if we compare the baseline with the final results. And we apply this for the cases for the project, where something like 10 cases, 1 month simulation, winter cases, and 5 winter cases, 5 summer cases. So, and we had the chance to do a better evaluation after the project. So here there's just some examples, precipitation from satellite, SWDAO also from satellite, and we have the chance to evaluate the ChemX model, for example, the integrated ozone and EOD. The EOD we calculate from the composition of PM 2.5, and we have a few findings, some stuff that we learn from this project. The first one, we have, of course, the configuration and a good model setup for provides good results for the region, but the main improvement is for data simulation that makes the biggest difference, the biggest improvement in the results. We evaluate the WRF against a lot of meteorological, and we find a very cold bias for some summer cases. So this is still a problem, but another caveat of that is most of the stations are in coastal areas, and this is a very dry region. And we have the chance, of course, to evaluate more systematically WRF with METAR and satellite data. We found out the cloud fraction is a very bad performance, and also cloud water path. This is not a surprise, but this was not a very important impact on the air quality simulations. And the COMEX results agree with the satellite, both in observation and magnitude of the pollutants. Right, thank you guys.
Thank you. Poster number 4.
Hi, I'm Lucy. I work at UC Boulder with Anish, but this is work that's been done with Valeria Lucarini at the University of Leicester in the UK.
Could you move a little closer to the mic, please?
Oh, sorry. This is what has been done with Valeria Lucarini at the University of Leicester in the UK. So we have developed what we call the convective timescale based on the variance of total column moisture and vertical convective flux, the details of which relate to a moisture budget are fully explained in my poster. And we use a case study of the Indian monsoon to show that the convective timescale approximately halves between pre and post onset. And there are various implications for the use of this, sort of regime changes under future climate forcing as a metric for model comparison or convective parameterization comparison. And that's it.
Number 5.
Hi, my name is Marta Moreno Ibanez. I work at CIRES and NSIDC. My work focuses on polar lows, which are small mesoscale cyclones intense that develop over the ocean at high latitudes during marine colder outbreaks, and you can see animates on the screen. So what I'm doing is I'm doing simulations with WRF with 3 different resolutions, so 50, 25, and 12.5 kilometers, because I want to analyze the impact of the horizontal resolution on the representation of polar lows in WRF. So basically, I'm doing these simulations, then I'm going to track the polar lows, and then I'm going to compare the polar lows across the simulations. And one thing I've found for now, if you look at one of the cases, is that the polar low is weaker in the coarser simulation compared to the higher resolution simulation. So if you want to see more about this case, just talk to me.
Not the different, yeah. Number 6.
Hello, I am Haruka Miura from Osaka in Japan. I am office worker, so not the scientist and not the developers. In order to test the accuracy of the WRF and SWAN models, wind speed, direction, and wave conditions were calculated using the models for Typhoon Sebi in 2018. The WRF simulations were done with 14 different microphysics schemes. Subsequently, wave conditions were calculated using the SWAN model with WRF and GSM. GSM is in Japan data. GSM wind data as input. Thank you.
Okay, number 7 is a virtual one, but yeah, you can bring up the slides and this.
Hi all, am I audible?
Yes, yes.
Hi, I'm Ananya, and I've been working on the role of upper level jet imbalance in the gravity wave of depression, which was organized near a complex terrain of US-Mexico border. So if we look at the Earth on any given day and the satellite image of it, we see a variety of clouds that are there and which like vary vastly in space and time. So our focus was only on the mesoscale, beta scale, which actually includes these gravity waves, which look somewhat like this, and they are 20 to 200 kilometers of scale. So they basically fall through the cracks in the GCMs, and that's why they are unresolvable. So we use subgrid scale processes and analyzing tools for it. So we looked at the double nested WRF simulation and tried to simulate these waves. And we focused on the case study of March 7, 2008, and looked at the large scale amplitude of mesoscale gravity wave, which actually affected the sensible weather over the United States. And we looked at particularly at the genesis, whether it was by the orography or the jet imbalance. So please check out the poster, and you can also scan it over here. Let me know the feedback and any comments you have. Thank you.
Number 8, please.
Hello, my name is Alexandra Stevens. I'm a graduate student in the Department of Physics at the University of Toronto, and I'm supervised by Professor Kent Moore there. This work centers around an extreme wind event in April 2005 in the Nares Strait, which is located between Ellesmere Island, the northernmost island in Canada, and Greenland. There was an ice camp that had been set up to study the area, but it was destroyed by this storm, so that's why we're studying it. We used the Copernicus Arctic Regional Reanalysis Dataset, also known as CARA, which has 2.5 kilometers spatial resolution, which is much better than ERA5 to analyze this event. We did a climatological analysis, and we found that on April 14th at midnight UTC, which is in the evening, the previous day in that time zone, the winds exceed the 95th percentile at the 700 to 800 meter level, and there was a low-level jet there. And we also found a similar timeline to the Melling paper that was published based on observations taken at the camp that was destroyed. And we also found that the most extreme observed wind speeds were still not captured by the CARA dataset. And so we're looking to get even better resolution to see if we can capture those most extreme wind speeds. Thank you.
Number 11.
Hi, I'm Yi from Script UCSD. For today's poster session, we would love to share our very recent study related to examining the impact of assimilating airborne radio occultation by using MPAS-A. So the airborne radio occultations is a very unique observations we obtained during the atmospheric river campaign. So how we use MPAS-A to assimilate those very unique data, and what's its added value by assimilating airborne radio occultations? And on the other hand, do we have any challenges and future work related to this study? Please visit our poster with the number 11, and we can have more detailed discussion about it. Thank you.
Number 12.
I'm Russ Bullock with the EPA in North Carolina. Last year, I presented a poster on some work I was doing, attempting to nest one impasse mesh inside another. A lot of people wonder why. I can explain that at the poster, but I've got that all packaged away now, and I'm putting this together in an actual, what I'm calling a software toolkit, where we've got 3 parts. The first is called GridGen, which will generate the points, the central generating points for the MPAS-A mesh. Then you've got make mesh, which takes the information from that run and actually creates your file, your mesh file for MPAS applications. And then I've got this third one where that's the nesting part, which actually works with the generating point sets of the 2 meshes that you're interested in putting together. And once that runs, then you run make mesh with the results of that to get your final nested mesh, where the outside background will match a global uniform or any other global mesh that you want to start with from the outside. So I'm poster number 12. Come on over and talk.
You 13.
Hi, I'm Janet Dorico from GSL. As Christina Holt mentioned at the end of the discussion yesterday, we use the unified workflow tools to build an MPAS app, which is a framework for exploring the MPAS model in both real-time and retrospective experiments. It contains a portable build system and will configure and run your experiment with Rakoto. Currently, it supports OnGrid, MPAS, which is to say MPAS-Init and MPAS-Atmosphere, as well as post-processing with MPAS-It and UPP. This is a relatively new project, so we've got a lot that we're kind of looking forward to, including regional and global physics development and configuration, ensemble design to support an ensemble forecast, as well as data assimilation with JEDI and MPAS-JEDI. So we're obviously excited to share this with you, but also very excited to hear from you as MPAS users and sort of how you use MPAS and what you might be looking for in an MPAS app to help you. So we're 13.
Thank you. Number 15.
Right. My name is Ligia Bernardet, and this is a poster about expanding the Unified Forecast System, or UFS, to include the MPAS Dynamical Core. And this is work that was conducted by a Tiger team composed of myself from NOAA GSL, but also colleagues from the Weather Service, Environmental Modeling Center, and NCAR, as well as Dom, who was at JCSDA at the time. So I think you already heard some about the Unified Forecast System here, this MPAS workshop. It is a community model, but it's also used for NOAA operations. It has a number of subcomponents. One of them is the FE3 Dynamical Core that's used in the global GFS, as well as a number of other components. And this graph here explains how, and I know you cannot see the details, but explains how the multiple operational applications run today by NOAA and SAP are planned to be simplified by using a more integrated system. However, when using the UFS with the FE3 Dynamical Core and the physics and all the other parts that we used for the 3-kilometer applications, some challenges were faced, and those were traced to the Dynamical Core. So this is just an example here. In the middle panel, we have the RRFS, Rapid Refresh Forecast System, showing that the storms were too bulky compared to the panel on the right, which is the MRMS reflectivity observations. So in this poster, can you advance for me or, okay. We will talk about our impetus to explore the MPAS Dynamical Core within the UFS. And that would be not with the standalone MPAS-A, but more like how NCAR is bringing the MPAS Dy Core into their CAM SEMA model. So we're gonna, if you're interested, stop by and I can tell you how we are planning to do that and what the challenges involved are. Thanks.
Thanks. Let's give our presenters a round of applause. You can go and grab a coffee or whatever. The viewing session is ongoing, so until about 5. Thank you.